Okay, yeah, Shankar sir, it is for testing, uh, for streaming in on YouTube. Can you hear me, Shankar sir?
Between I can hear, but I cannot speak. My
Okay, sir. You can. So I am just giving my microphone to you. Okay, thank you.
Because if you disable my microphone, you just enable it.
Okay, just I am disabling you.
this kind of methodology. So now what we are going to see, that suppose that I have no knowledge of mechanical engineering, I have no knowledge of electrical engineering, I have no knowledge of finance, and suppose if I have certain given equations, then how to analyze that, how to modify that. So without knowing the system, if I know just some objective, it is possible to modify the system using the knowledge of the system theory. So the purpose of discussion, introduce the audience to the axiomatic way of development of system theory. So I have already told you that in this lecture, I'm not going to talk about the calculation oriented things. Most of time, I'm going to talk about generalized theory. And obviously, means axiomatic way of thinking is not obvious. So I have to give lot of examples in order to connect with the axiomatic representation of the system. And I hope that after the completion of this lecture, audience will be familiar with the structure of axioms, definition, proposition, theorem, lemma, and I hope that means whenever you are reading books or papers, these kind of things frequently come in front of us, and most of time we become very much annoyed if we are not knowing these things or difference between these things very much carefully. And actually, if you understood the structure and how to write, suppose that how to write definition in proper way, and I will tell you some example where people are just coining the improper definition in sense of the system theory. And after that, sometime whatever theorem people are proposing, that is not appropriate, and why that is not appropriate I will tell you. And after that means two important things, that is connectives, quantifier, and some kind of conditional or biconditional statements. That is very important. And if I have time, then I will talk about the methods of proof. So basically, if you understood these kind of things, then I hope that it is very useful to development of the new theories for a class of system. So class of system means now you can put mechanical system, electrical system, electronic system, biological system all inside one bucket and develop same kind of theory. So using one lens, now you are able to see a whole picture. So there is no need to worry about mechanical, electrical, electronics, or all other kind of knowledge. Just fundamental equation is enough to understand the future development of the theory. And most of time, I am not going to talk about quantitative analysis. I am going to talk about the qualitative analysis. So these approach are very much useful for the qualitative analysis. And obviously, those who are working on game theory, computer science, and information theory, machine learning, so these kind of concept is also helpful to them. So let us start the lecture. So first, what is my first concern? My first concern about the system. And whenever you turn on your book or any research paper, most of time people are talking about the system. And if you try to see the definition, so that is very vague definition. For biological people, meaning of system is different. For chemical people, meaning of system is different. For finance people, meaning of definition means system is different. And but this word is frequently people are using without properly without giving the proper definition. And this is same like whatever figure you can see that I have one elephant. So whenever people are seeing, suppose all people are blind, so they are seeing from their own prospect, and due to that reason we have several different definition for the same elephant. And honestly speaking, that using one definition one cannot cover everything. So I have to fix definition for the system theory. So at least I am assuming that this particular definition I am going to follow for system theory course. So let us see the examples of systems. So a computer, a robot, a human being, all are, we are talking that that is somehow an example of the system. But by seeing the example or by reading the books, what happens that it make seem as if absolutely anything is a system. Means whatever things we are seeing, that somehow we are telling, we are feeling that that is the system, but that is not the case. Suppose I will tell you that why whatever example I have given that is not a system. We are telling that a painting, a rock concert, a footy match, a can of baked beans, these are not the system. For at least for our purpose, these are not the system. So somehow I have to make the definition such that I have two class, something which fall inside the bucket and something which fall outside the bucket. And meaning of definition, whenever we are giving definition, it means that if something is understood using definition, then something lie inside the set and something outside the set. So for us, this is the meaning of the system. So what we are telling that whenever we have some system, then what we are going to do, first we can perform some kind of measurement on it and get out with unique number. You can see that one word I am giving lot of emphasis, that is unique number. So whenever I have something and if I perform measurement and if I get some unique number, then I will tell or I will define that particular object as a system. So using this definition, I'm going to proceed for the next slide, and I will give you mathematical one also. But this is the meaning of system for my understanding. And if you believe on this definition, then you are able to understand system theory, machine learning, or means or control system, or whatever means engineering, core engineering quantity, you are able to understand using this definition. And if you see this number, this is not just a number. They tell us things if we listen to them. Suppose that if we went to some doctor or physician, then how basically they are guessing about our disease. They collect our blood pressure, sometimes they collect our temperature, pulse rate, and after that, after getting this, they are conclude something else or some kind of variable, or in between they are asking some question. So you can see that I am collecting several number and analysis of that number. Basically, we are predicting something. So in that way, number, whatever number that is coming after the measurement, that will tells about some particular system. Or suppose that if I have disease, then using that particular number means blood pressure, temperature, pulse rate, or some other question, doctor is able to estimate what kind of disease I have, or I am healthy or not. So what is importance of numbers? So somehow what we are doing now, we are making measurement, means we are applying some kind of input to some object, and after that we are getting some unique number. So basically, how basically we are developing the model of something. Suppose I have capacitor, so I am going to apply different voltage across the capacitor, and at each and every instant I am going to measure the value of current or value of charge which is developed across the capacitor. And after that, after analyzing this number, or take very simple example, suppose you have some resistor, you apply some voltage, and after that I am calculating the current, and using the data of voltage and current, somehow I am going to talk about the resistance. And these kind of experiment basically we are doing during our bachelor first year bachelor program. So somehow using number, I am going to talk about some kind of invariant quantity inside the system. So you can see that voltage is varying, current is varying, but property of some unique property, we are able to talk about the system. So somehow we are telling, okay, that using that unique quantity, we are going to model that system. We are telling, okay, whenever voltage will apply, then how basically current is related to the voltage for the case of resistor. So, and if by using that experiment, if that is true for large class of system, then somehow that particular model is promoted to the theory. So suppose that you can just take example of the Newton's law, and Newton's law is very means one of the favorite law for me. So what we are doing, whenever we have motion, certain kind of motion of rate or rate of change is involved, it is possible to show that some quantity like position like quantity, some velocity like quantity comes into picture, and there always exists some kind of relation between them. So basically, a theory may tell you what sort of model to use in a particular case. So if after doing experiment you are getting some kind of invariant quantity, suppose that after doing the experiment we have detected the resistance, similarly for capacitor we have detected the capacitance, similarly if you do some kind of experiment, you have some mass, you can apply some force and get and note the velocity, acceleration, and after that try to estimate the mass. So in this way we are formulating some new theory. So this way of formulation of theory, which is based on the measurement of number, is quantitative way. And what happens that somehow we are noting the change. So now after doing finite number of experiment, we are telling that okay, this kind of theory will work, and after that we are generalizing that that theory. So using numbers we are able to understand about the system. So that is the conclusion. Now let us come to the mathematics, because what happens that I have some physical system, and after that what we are telling that in place of physical system, now I am going to substitute with some kind of mathematical model. Means now I am going to talk about abstract quantity, and believe on me that physical quantity and abstract quantity is not always same. That always exists some kind of difference between physical quantity or their representation or some kind of abstract quantity. So what basically we are doing, I have capacitor, but I am going to represent that capacitor using some kind of mathematical equation. I have some kind of resistor, I am going to represent that using some mathematical equation, and this way is very much beneficial for us, because doing realistic experiment required lot of money, lot of effort, lot of places are required. But if you are able to capture that physical object using some kind of abstraction, then experiment become very cheap. So, and in that way you are able to think about new quantity even if that physical quantity is not existing to us. And so due to that reason, mathematics give us lot of scope to think about the new system as well as the analysis of the old system. So let us see the way in which mathematician is basically thinking. So what mathematicians are doing, they collect information, make some kind of observation about some particular phenomena, and try to build some kind of theory, and that is nothing but we are telling model, and somehow we are making some kind of relationship between quantities and structure. So suppose that first, in order to establish the relation, for example, if you again take the example of the capacitor, where first they have defined, somehow they define what is meaning of charge, what is meaning of voltage, and after that, after doing that, they are seeing that how basically voltage changes with respect to time, and based on that they are making some kind of relationship and developing some kind of model. So this approach of development is called inductive reasoning, and somehow physics people is also following this way. Another way is the deductive reasoning, based on deductive reasoning, and mathematicians basically follow both kind of reasoning. Mathematician means I'm also talking about those who are working on applied mathematics. So if you see the means most abstract thinking of the mathematician, that is basically deductive thinking. So, and here in that part of thinking, basically we are going to use the logic, and I will come up the logic in the next part of my lecture. So basically what we are telling, that whatever second group of mathematician, so they are first assume something, so they are accept something as a truth, and based on that truth, after applying the logic, they are going to develop some kind of theory. So means you can think like this. Suppose that you have one capacitor and you have performed some kind of experiment, and after that what you found that current I is C dV by dt. Now suppose that if I have n number of capacitor, and if they are connected in series or parallel, I hope that you are already knowing that what is meaning of series connection or parallel connection, then still using logic, I can tell that if n number of capacitor is connected in some fashion, then what is equivalent to them. So in that way, means after accepting something, so we have accepted that whatever charge across the capacitor, that is Q equal to C multiplied by V. So this kind of things I have accepted, and after that we are basically driving the theories. Similarly, suppose that now let us talk about mathematician. So they have accepted that okay, number is represented like 1, 2, 3, 4, 5, 6, and after that they have given several means axioms to understand. I will tell you what is meaning of axioms, and after that they are telling that how to manipulate that number. So first we have to accept that there exists some kind of number which is equally spaced, like 1, 2, 3, 4, 5, 6, and between them there exist several numbers. So we are accepting something as a truth, but we are not checking, just we are accepting something as a real line, and after that we are developing the theory, and this way of thinking is called deductive reasoning. So let us try to see the difference between abstract mathematics and other science. So in laboratory science, I have already told you that how basically scientists are developing the theory. They are performing the experiment, and after several experiments, we are proposing some kind of observation or theory. But if you see the mathematician, so actually what happens, they are taking some information from the experiment or computer simulation, and after that, using some kind of logical argument, they are making something which is applicable for large class of system. And in order to do that, because we have to collect several things, and after that we have to form a structure and some kind of relation. So due to that reason, we have to accept something, and that is nothing but axioms. And whatever approach that applied mathematician or abstract mathematician are using, that is called axiomatic approach. So basically, let us try to understand what is meaning of axioms. So in studying abstract mathematics, because somehow we are using abstract mathematics to capture our physical system. So I have original physical system, now I have abstract representation of that system. So due to that reason, I am restricting myself on abstract mathematics only. And what I am telling that in studying abstract mathematics, we take what is called axiomatic approach. And in this approach, basically we are collecting the object. So whatever example I have taken, in case of capacitor, I have collected the charge that is in one set. After that, I am collecting the voltage inside same set. I will collect the how to define rate of change, and after that I have also collected what is the invariant quantity, means capacitance C, that is the property of that capacitor. And after that we are formulating some kind of rule. But before formulating the rule, I am assuming that okay, whenever I will connect with some kind of voltage source, then some charge is developed across the capacitor. So we are accepting. Now we are not checking that why charge is developed, what is reason for development of charge. Just we are assuming. Again, if you go in more deeper, then at that time you have to characterize the charge also, and we have to tell that okay, whenever charge will develop, then charge will develop in quantized fashion. Means minimum value of charge you have already learned that 1.6 10 power minus 19, like that, something like that. So again, that is more deeper quantity. So but if you go deep, then it is very difficult to come with the concrete thing. Due to that reason, we are accepting whatever things is well established, and after that we are developing some new theory. So whatever our blind acceptance, that is called axioms for that particular system or particular phenomena or particular structure. And so what we are telling, that an axioms is an assumption, again that is assumption, that we agree to make, usually because everyone agree that it is sensible. So sometimes means whenever we are talking about physical system, so we are assuming that after connection of voltage, some charge will develop. So we are accepting it, and somehow physical people are using some kind of experiment. They are also demonstrating that. But for mathematics, sometimes means people are not worrying about the demonstration. And after that, you can see that second things I have written. We do not try to prove axioms, because that is unnecessary wasting of time. Most of time, somehow we have to start somewhere. I have to start where means I cannot actually able to prove something. And an axioms is something that we all agree to assume is true, so that we can get on with using it is more interesting thing. And if you see that this approach, and I hope that whatever religion that is developed inside this world, somehow that is also based on same principle. First, we are assuming, means if you see the structure of some religion, they are thinking that you can believe on something. So we are believing this some source of energy, but we are not going to check that God exists or not exists. So first you have to assume that God exists, and after that, after the consequence of that, you feel that is consequence of that is always beneficial. Again, another set of people which believe that God will not exist. Again, for him, some lot of good thing comes into picture. So either you have to believe or not to believe. But if you become confused, then things become more complicated. So somehow axiomatic approach is telling that either you can believe or not believe. So let us now come little remark about the axioms. So whatever axioms, because I have already told you that in order to form some theory, I have collecting lot of object, and for each and every object I have some kind of theory associated with that. In case of charge, I have some theory. In case of voltage, I have some another theory. So somehow whatever axioms we are assuming that is consistent, means that should be not contradict with one another if we are going to correlate some classes of things. And second important thing, that too many axioms is not required. So try to work with minimum number of axioms, because in order to form some theory, you have to check back that axioms is satisfied or not. And again, axioms should not be much restrictive, otherwise your scope of your theory become limited. So due to that reason, means whenever you are developing some theory, please try to see the axioms, try to see the assumption very, very carefully. Now, and I will tell you here one interesting example, that suppose that if I am telling that if I build some kind of a stair which has infinite length, then I can climb to the moon. And means logically this statement is okay, but you can see that it is very difficult to verify this assumption. Means I cannot build some kind of a staircase which has infinite length. Now let us come to the important quantity. I have told you that whenever we are talking about axiomatic way, so I have to believe, and I have believe can be either you can believe and not to believe, means I have just two things, either true or false. So that kind of quantity is called a statement. So a statement in logic or mathematics is an assertion that is either true or false. So I cannot confuse between true and false. If we will confuse, then that is not the part of axiomatic mathematics. There exists some kind of logic where I cannot able to decide what is true or false. That is called fuzzy logic. And somehow I am not going to talk fuzzy logic in this course, because I cannot able to give guarantee. And here you can see that either I can tell true or false, so I can give guarantee about this. So here you can see that I have taken some very simple example. So 2 plus 3 equal to 5. So this is a statement because this is true. 2 plus 3 equal to 6, that is again a statement, but that is false. And all cats are black, so it might possible some cat may or may not be black, so it might possible that either this is true or false. So due to that reason, it is again a statement. So whenever we are talking about mathematical statement or a statement in engineering course, that always belongs to this, because whenever we are talking about engineering quantity, that is fully inspired from the mathematics. So we have to actually remain consistent with respect to mathematics. Let us try to see some more quantity, that is called expression. So basically a statement are different from the expression. So whenever we are writing 2 plus 3, that is one kind of expression, but 2 plus 3 is true or false, that depends on the result. So 2 plus 3, if someone writes 6, then that is false. So 2 plus 3 is basically the not a statement, that is just a expression. So whenever we are talking about the expression, at that time we are talking about the numbers, matrix, function, set. We are not talking about some kind of conclusion. So this is the difference between the statement and the expression. Now, before going to understand the exams carefully, I am going to take you one very simple example of the mechanical system. And why I have collected this example, because I will tell you that you all are already well aware that I have two different approach of the control system, that is classical control theory or modern control theory. So classical control theory is somehow inspired from electrical engineering, or whatever modern control theory, that is inspired from the mechanical engineering. And if you read the first paper of Kalman, that is the same paper, and he clearly wrote that whatever things that I am going to develop, that is modern control theory, notion of state, notion of dynamical system, that is fully inspired from the mechanical system. So somehow that is motivated from the whatever mechanical theory developed inside the literature. So due to that reason, I have taken this particular example. So I am assuming I have some mass, and that mass on some surface, and I am assuming that there is no friction force, and here f may be function of time or function of position, or may not, that is just function of time also. So in this particular equation number 1, you can see that I have means written like this. So let us now come here. Whenever you are writing this equation, you can see that I have actually make several kind of assumption, several kind of axioms also. So what is, first try to understand the assumption whenever we are writing this equation. And I hope that you all are believe that this equation is basically come from the theory of the theory of the Newtons. So using Newtons, so what Newtons was telling that if I have some configuration is changed with respect to time, then always there exists rate of change, and that is equal to the velocity. So here you can see that I am assuming that whatever position x, that is differentiable with respect to time, but you can plot several graph which is not differentiable. At that time I cannot define the velocity. So whenever you are defining the concept of velocity, then somehow you are assuming some, means hidden assumption is here, that I am pretty assuming that xt is continuous. And apart from that, I am telling that not only continuous, that is differentiable also. And whenever we are defining velocity, again I am taking differentiation of vt. So again I am assuming that not only one time, that is 2 time differentiable. So these are the assumption, or these assumptions are somehow axioms, because everyone is believe on this. Without believing on this, I cannot proceed towards the Newton's law. So somehow I can either, you can believe on as a assumption or axioms. And I have already told you that axioms is nothing but those kind of assumption which is accepted by large group of people. And so in that way, you are able to identify the assumption. Now suppose that I have to identify the position. I have to calculate the position here because ft is changing with respect to time. So now I am going to calculate the position of this system. So what I am telling, I will perform one measurement. Suppose that I have to estimate the mass of this mechanical object. So what I am going to do, first I am going to apply some force, and corresponding to that force I am going to calculate, I am going to detect the distance, and in that way by plotting it, somehow I am trying to guess the value of mass. Suppose mass is now given to me, and now if I apply some unknown force, then it is possible to define the position. So somehow here what we have observed, that I am believing that xt is two-time differentiable. Another assumption is that whatever mass I am assuming here, that is point mass. If I will not assume that point mass or whatever, if that is distributed, then I am assuming that all mass, equivalent mass, is put at the center of mass, and both are equivalent. If you do not believe on this assumption, you are not able to apply Newton's law. What is another assumption? We are assuming that this whatever object that is rigid one, it means that distance between 2 points is always remains the same. So that kind of assumption I am assuming. So you can see that in order to develop one Newton's law, I have made several axioms, and based on that axioms, I am able to formulate this law. And in order to know, you can see that if you want to calculate the velocity, then you can take the first integral again here. Since I have applied force ft after t0 time onward, but before that I am not knowing what kind of environmental force, what kind of inside force is acting on the system. Due to that reason, I have to break this integral into two parts. One part is minus infinity to t0, and another part is t0 to t. And you can see that this part, which is 1 by m at minus infinity to t0, means very large information we are telling, but finally we are getting with some number vt0. So if I know this number vt0, means if I know initial velocity at t equal to 0, then I can always predict the future velocity, because I am assuming that m is not known to me, ft is known to me. And in order to predict the futuristic state, now you can see that I need information of initial time, I need the information of initial position, initial velocity, and after that this quantity 1 by m d tau t0 to t f tau, I am assuming that is known to me. So in order to predict xt uniquely, I need two set of information, and that set of information is nothing but the state variable of the system. So somehow if you interpret a state, then that contain information from minus infinity to t0. So a state at t0 is somehow summation of all information, or somehow an energy carrying variable up to that t0 time. So what we have observed in this example, again come to this mechanical system. So I have some system, I am performing, I am giving some kind of real input ft, and after that I am getting real output, that is x tau. And in this way, lot of internal quantity is involved, and that quantity is somehow displacement xt0 and velocity vt0. And if I know the displacement at t equal to 0 and vt0, then I can predict the future. Now let us come to the dynamical system. So this is one experiment. After that, what basically Kalman is claiming, that now you can take any system and you can apply force and try to note the output. So whatever measurement you are going to perform, I hope that you all are agree that whatever instrumentation I have developed till now, that is only able to read the real quantity. So they are not able to read any complex quantity. They are always able to read some kind of real number or even any function. So I can interpret function as a series of real number matrix, as some kind of real number again distributed across the n cross m matrix. So somehow whatever input or whatever measurement we are going to perform and whatever output I am going to get, both are the real number. And due to that reason, one course that is related to real analysis is one of the most important course for those who are working on system engineering or control system. So now let us see that he was telling that any system is called dynamical system, provided you can apply some real input or you can perform some measurement. And whenever we are performing measurement, then we have to note the input, and after that we have to record the output. Again, that is real. And so if that will exist, then I will tell that okay, that is the necessary condition for the existence of the dynamical system. And after that second condition, you can see that what they are telling that YT means whatever output that is function of the input, not futuristic input, that is either function of the present input, or I can some case I can assume that that is function of past input also. But I cannot build some kind of system that is again function of the future input. So that is the restriction in our case, but that is not the restriction in finance, because you all are knowing that this is the situation of COVID. So, and if we know that some share price is going to down, then I am going to withdraw the money. So somehow our current decision is affected by the future definition, future incident. But this is not the case in the dynamical system. So due to that reason, using these two axioms, so you can see that number of axioms is finite. Things are pretty clear that input is real, output is real, and whatever output that is not the function of the future value of the input. So using these two axioms, I can define the dynamical system. And obviously, what we have observed in the previous example, that if you want to define YT uniquely, then you have to understand something more. And due to that reason, definition of state comes into picture. I will again tell you that how to write definition, but in order to show something, I have to means actually bring here the definition. So the state of an object, abstract object, again I am telling that that is not our physical object, because I have modeled that object after several axioms, several assumptions I am going to capture with some kind of mathematical equation, and that is abstract object, that is not same as physical object. But I can tell that means whatever input output of the real object and abstract object, that is same. Somehow we are telling that. So the state of an abstract object is collection of number which together with the input ut for all t greater than equal to t0 to uniquely determine the output yt for t equal to t0. So now next question, you can see that what is my goal, given that we have dynamical system. So whenever now I am going to tell about dynamical system, then that two axioms comes into picture, means input output is real, and whatever output that is not going to depend on the future input. So given that we have a dynamical system relating yt to ut means input output, we would like to construct a set of mathematical relation defining a state. Because in mechanical system, what we have seen that suppose I have force Ft and I want to predict xt, then I have to know some kind of quantity, that is xt0 and vt0. Then only I can predict the output is their position. So due to that reason, I have notion of this kind of notion. Now let us come to the next part of this lecture. So next part of this lecture is, so what we have found that I have some system, I have input and output pair, and inside something. So we have to fix the axioms such that I can take the proper value of the state. And in order to do that, actually I have output, I have input, and in between I have some value of a state. So again, I have to fix some kind of axiom such that I can define the state, because representation of input and output is unique, but it is possible to show that a state representation is not unique representation. Why? Suppose that I have some input data, I have some output data, and I have to make some kind of function, because whatever machine we are assuming, that is function, because we have to maintain uniqueness of output, and whenever we have to maintain uniqueness of output, then whatever intermediate quantity, that is a function. And definition, whenever we try to define some function, then we have to consistent with respect to the definition of function. And due to that reason, even if there are infinite many ways to correlate between input and output. Hello. So there are infinite possible way to correlate between input to output. But whenever we are defining the internal quantity, then again we have to assume something, and I have to assume five things. Then only I can tell that 5 different quantity is satisfy the condition of the means together. Means if I believe on axioms 1, axioms 2, axioms 3, axioms 4, axioms 5, then I can able to define the notion of a state. And for time being, you can do not go to all means axioms. Just I will tell you the meaning. So axioms 1 is telling that output is always real, and output is some kind of function eta, and that is depending on t, and phi is nothing but the state and ut. And what we are telling that trajectory is unique for each and every time. So somehow if we lose the uniqueness, then that become that create difficulty. And the third is also talking about the unique trajectory at some time when t tending towards t1. And axioms 4 is talking about the transition property. What is meaning of transition property? That if you start your experiment at t0, and if at that time your state is xt0, then after t time, if you are moving to xt1, then and after that if you are moving to xt2, then for x2 t2, in order to create x2 t2, either I can assume xt1 as a state or xt0 as a state. So somehow there exists some kind of connection between xt0 and xt1. So that property is called the transition property. And assuming that whatever state, again, that will not depend on the future value of the input. So if you believe on these 5 axioms, then I can define the state. So let us again come back. So for dynamical system, I have to believe on 2 axioms, and in order to define the state, I have to believe on these 5 axioms. So now you have any system, mechanical system, electrical system, electronic system, finance, whatever you can take. And if you consistent with these 2 axioms for dynamical system or 5 axioms for the state, then I am telling that is axiomatic representation of the system. So now I will give you some counter example, and you have to check that is system or not. So suppose here I have just taken very simple example, yt equal to jut, where j is square root of -1. It means that I am representing some system where input and output, input I have and output ut, and that is related with this equation. So you can see that if I assume input as a real number, then obviously automatically what happens? Yt become complex number. And vice versa. If you assume yt as some kind of real number, so in order to maintain this relationship, again ut become complex number. And due to that reason, this doesn't represent any abstract system. So yt equal to jut. So by using this story, so this is simple story, but you can see that second story is a little bit more interesting. Now suppose that I have dynamical system dyt by dt equal to ut. I am assuming I have single input, single output system, means ut belongs to R and yt belongs to R, means all input on real number, and yt, whatever output I am getting, that is also on real number, because in order to satisfy the property of dynamical system. And again, using the dynamical system, it is possible to show that yt do not depends on the future value of input. Due to that reason, whatever dy by dt equal to ut represent the first order single input, single output dynamical system. Now let us come to the state space representation. You can see that now I can rewrite this system like this: dxt by dt equal to jut and yt equal to minus jxt. So, and if you substitute this quantity here, means dy by dt, then automatically I will end up to the dynamical system. So now here you can see that even if I will do space representation using some kind of complex quantity or imaginary quantity, still my input output remains the real. So due to that reason, this represent the means whatever dynamical system, input output is real. State space representation may be complex. So if you understood the exams very much carefully, then now you have another scope. Now if you have system, so most of time I hope that most of you may believe that whatever state space representation, that is only xt belongs to real number or rn. But here now we have flexibility. So if you assume means understand exams in a very much careful way, then you are able to develop new notion. So here what I am telling, that dynamical system means the dynamical system always satisfy two axioms. Whatever state space representation, that will also satisfy all 5 axioms, and it is pretty easy to check by solution. I am not going to do that because it will take a lot of time. And so in this way, if you understood the axioms, you are able to create new theory. Now up to here, what we have seen, that what is importance of axioms. So due to that reason, you have to become very, very careful in order to understand the axioms. Now let us come to the definition. And whatever definition we are telling, definition in mathematics, that is different from the ordinary English definition. And I have taken a very simple example because most of time you may have seen that in college life people are using that you are a very cool person. But here definition of cool is different than as usual definition of the English. But that is very much popular. Then we are frequently using that you are a very cool person, or like you are very cool or something like that. But definition in mathematics has precise and fixed meaning. So in whatever example I have taken, that depend on the context. So if I am telling that some person is a cool, then we are understanding, okay, means what is meaning of definition of cool, that depends on where you are basically located. So that is not universal definition or precise definition, because meaning of cool is something. Suppose we are telling that means climate is very cool or something like that, and automatically here person become cool. So definition is very, very vague. But in mathematics, everything is precise and fixed meaning. So whenever we are telling something as a odd number, then that is not strange. We are knowing what is meaning of odd number, and that is equally valid in all states of India. Everywhere in this world, people are understanding integer is odd in same way whatever we are understanding here. So somehow means whenever we are talking about odd number, so mental picture is like that 1, 3, 5, 7, 9 or something. So this is just a mental picture, but that is not the concrete definition. So basically we have to define something, and in the latter part of this course I will tell you that whenever we are defining some definition, then one connective is very, very, very much required. And at least now onward, whenever you are proposing new definition, or whenever you are means reading some new definition, try to understand that where this connective is involved, and that connective is if and only if. So this connective is required whenever you are defining some quantity. Now let us come to the definition. So here you can see that I have in order to understand the definition, I have taken a very simple example. So suppose that means during childhood you may have learned like this: a number is even if it is divisible by 2. And but when you come to the means particularly during your PhD, when you come to the system engineering course, at that time professor is not going to write definition of even number like this. They are going to write definition like this: a number n is even if and only if there exists an integer k such that n equal to 2k. So now you can see that means if you see the context, then definition first, whatever we learn during childhood, that is and what is meaning, that is in second definition, both are same. But now I am telling you that second definition is more precise. Why that is more precise? You can see that in first definition, even is when it is divisible by 2, clearly that capture the key idea, but it is not precise. And because here you can see that I do not know what is number here. So actually what happens, we are not become so much precise in first definition. But if you see the second definition, then they are telling that n is some kind of number. So that is very, very precise. Now after that, so this is about the precision, means whenever we are taking number, we are talking about what kind of number. So I am taking, okay, some number n, and at this moment I am not worrying about that number. And after that we are means talking about an integer k such that n equal to 2k. So everything is very, very precisely written. And I have already told you that whenever we are writing definition, at that time we are using if and only if in order to do more precision. It means that if and only if, I will tell you the more meaning of if and only if in the next part of this lecture. But here what we have understood, that if I write n equal to 2k, then automatically that is even number. And if n is even number, then that will satisfy n equal to 2k. So that will work in both directions. And that is the meaning of the definition. And if you see the means operational way of the definition, means if you believe on second definition, then proof become very, very easy. Suppose that you have to prove that any integer multiply of an even number is also even. So now you can see that and if I will take the help of second definition, then I will assume, suppose that n is a even number, and from the definition I can understood n equal to 2k. And after that we are assuming z be any integer, and after that we are multiplying both sides by n, and by using the rule I am able to tell that, okay, z into n can be represented like this, and due to that reason, means this is again on the required form of definition, and due to that reason what I am telling, that whatever definition I have done, so using that definition I am easily able to prove something. So if you write definition using if and only if, most of time they are very good to prove some new quantity, new phenomena. And here I will give you the one example from, again, that is from system theory, that means why this definition is imprecise. So a system is called nonlinear system if it is not a linear system. And I hope that most of you may believe on this definition. And somehow this definition gives good picture. They are telling that, okay, linear system. So let us see the definition of linear system. Again, I have told you that whenever we are talking about system, it means that that is dynamical system somehow. So we have input and output data, and inside input and output I have some internal variable that is called state. So I have input state pair, that is xi, ui, and yi as the as the output. And after that, that should be satisfy the two property, additivity property and homogeneity property. So you all are already well aware about this, so I'm not going to waste my much time on this. And after that we are telling that this is the superposition principle. So if superposition principle will not satisfy, then sometimes people are telling that that as a non-linear system. But why that definition is imprecise? Because try to go inside any book, any research paper, whatever theory you are going to develop for non-linear system, in a special case, that theory is always valid for the linear system. But whatever definition we are making, why I am telling that is imprecise? You can see that a system is called non-linear if it is not a linear. It means that whatever non-linear system and linear system, we are making clear-cut boundary. But that is not the case. Whatever theory I am going to develop for non-linear system, that is equally valid for linear system. Then how that is means separated from that set? So due to that reason, I am telling this definition is imprecise. So what is correct definition? So I have to write like this: a system is called a nonlinear system if it is not necessarily a linear system. It means that even if superposition principle satisfied, then that is also a nonlinear system. Even if that is not satisfied, then that is also a nonlinear system. That is the meaning of, precise meaning of nonlinear system. And all mathematics book, means like Khalil, nonlinear system by Khalil or Slotin, that is believing on that definition only. A system is called nonlinear if that is not necessarily a linear. Means if superposition principle will satisfy, then that is also a nonlinear system. If that is not satisfied, then that is also a nonlinear system. Now, so in this way, definition is very, very important. And now I will tell you the another understanding of definition. And I hope that whenever first time you see the definition of limit or definition of stability, you become very, very much annoyed. And you are and these kind of definition create a very much mental picture that I cannot understand the stability, I cannot understand the limit, or like that. And when first time I have read this definition, honestly, I'm speaking, I'm not able to understand the meaning of this definition. So mathematical definition, because we are not knowing a lot of things, due to that reason, we become annoyed whenever we are seeing this kind of definition in the literature. And why I have selected this definition? Because based on this definition, I can talk about continuity, I can talk about stability, everything. So let us first try to understand the definition of limit. So what I am telling is that suppose I have some function fx, and if there exists some limit L when x tending towards a, and that is if and only if, again this is definition, so if and only if is required. So I am telling that for all, this symbol which is inverted of a, that is called for all. Again I will come, because this is the conditional, somehow this is called quantifiers. So quantify that for all epsilon greater than 0. So you can take any epsilon, there is no restriction on that. But second one, there exists a delta. So now you can see that means whatever inverted, means if you take E and put one mirror in back plane, then you are getting this kind of image, that is called there exists. So there exists a delta greater than 0, such that now they are telling that if x minus a lie between 0 to delta. So suppose I have real line, because I am talking function fx that belongs to just means that is real valued function. So whatever x, you can put any real number, then fx we are getting some kind of real number. And due to that reason, I have taken absolute value, because absolute value is telling us what is distance between x and some generalized quantity a. So here we are telling that x minus a lie between 0 to delta, and then fx minus L. So x, you can apply function on x, then you are get fx. You can apply function on a, at that time you will get L. If that will satisfy this kind of condition, then we are telling that the limit exists. This kind of limit exists. And in order to understand this definition, you try to see this figure. What I am telling that, okay, I have some function y equal to fx. So I have x argument, I have y argument, and after that, what you are telling that I am going to relate with this particular definition. I am going to check that at a x equal to a, this function is means this function has limit or not. So what basically we are going to do, first you can see that in this statement, whenever we are telling that fx equal to L is some limit, if and only if, first I am selecting the epsilon, and somehow we are telling that for all epsilon, and here you can see that epsilon is fx minus L less than epsilon. It means that I have x as some input, and after that, that will generate some kind of output y, that is y equal to fx. So here x works like input and y works like the output, and y is nothing but fx. So somehow first I am talking about the bondness of the output. So I am telling that if output is bounded by some epsilon, and if corresponding to that our input is bounded, then we can tell something. So what is general? First we fix the value of epsilon, and we are telling that corresponding to epsilon there exists some kind of delta. So basically we begin from the epsilon, and after that we are try to find the definition of the delta, and after that what we are telling that, okay, once we find a value that works for one delta, then for all a smaller value of delta that will work. So let us see, try to understand from this figure. So here I am at this point, so I am going to fix that value L, and after that I am going to see the variation of L along y-axis, so that is epsilon, and corresponding quantity I am going to see on x-axis. So, and based on that, what I'm telling that if I deviate L from plus minus epsilon, then and if that deviation is plus minus delta only, then basically I'm telling that if now delta tending towards 0, so basically we are tending towards A, and at the same time what happens if epsilon tending towards 0, then we are tending towards L. So in this way we are defining that this function is continuous, or means this function has a limit at L equal to A. But if we are not able to find the corresponding to epsilon, if we are not able to find delta, then we are telling that limit will not exist. So so this is the somehow interpretation of this, and let us try to see that how to find epsilon and delta. So I have taken a very simple example, and actually finding epsilon and delta is not so straightforward. I have taken very simple example. Suppose that I have ln x, so I have logarithmic function x, and I am telling that x tending towards A. At that time I have ln A. So now I am going to prove using epsilon and delta that whatever things I have written, that is true or not. Otherwise I cannot write limit x tending towards A, ln x equal to ln A. So I have already told you that first I have to fix the output. So I have to start with our output, and somehow output is related to epsilon, and after that we are telling that find delta which depends on epsilon, so that this relation will satisfy. And so I have to start from the output side, and somehow I have to come up with this relation, and in order to come up with this relation I have to do some kind of manipulation, and for that this particular problem I'm going to use this theorem, and I hope that during 10+2 you have already learned about mean value theorem. And what is a statement of this theorem? For sake of completion I am going to repeat here that fx is ln x, then and if that is continuous between A and B and both are positive, and fx is continuous on the closed interval A, B and differentiable, then we are telling that there exists some point C such that this relation will hold. And using that kind of relation, I am getting this. So if you read this, means I will give you slide. After that, try to read this, because I'm not going to waste much time on the calculation. And after that, you can see that I have two different limitations now. It might possible x is greater than A. So I am approaching from the left hand side. I am approaching from the left right hand side to the to some point, and due to that reason we have to consider two cases. And in first case, now I am come up with one delta is A epsilon. So we are telling that for delta equal to A epsilon, and epsilon you can take anything greater than 0, then there means corresponding to epsilon I am able to find delta, and then this relation will satisfy. Due to that reason function has limit if x greater than A. Now you can consider x less than A, and again you can do same kind of manipulation, and you can again see I have able to find some kind of delta in terms of epsilon. And in this way we are telling that corresponding to every epsilon there exists some kind of delta, because there exists some kind of equality here. So due to that reason this kind of relation will hold. So in both direction we have to prove, and after that we are getting that limit x tending towards A, ln x equal to ln A. So same kind of things we are going to talk, means now I will tell you that why I have selected this example. You can see that if you remember the stability, in first I will talk about the stability in one dimension. What we are telling that, okay, I have some system, I have input and output. So meaning of stability is somehow if output is bounded, so after that we are telling that corresponding to output, that output there exists some kind of input, bounded input somehow. And for linear system we are telling bounded input, bounded output stability. For nonlinear system it is not obvious, but some class of nonlinear system again we can take tell like this, and that is called input to state stable. So basically we are taking help of this way only. We are telling that means at x equal to 0 I will come up the definition of stability in next part of this means lecture, and there I am going to show you that similar kind of structure is actually maintained, people have maintained there also. So main crux of the idea, they are telling that if output is bounded, so corresponding to output there exists input or not. If there exists input that is bounded, then system is stable, otherwise that is unstable. So like that. So till now what we have seen that I have some system, So and I am going to assume something that is true everywhere, and that is called axioms. And after that I am talking about the statement that is either true or false. And after talking about the statement, what I have seen that definition, which is very, very important quantity, somehow definition tells us that how something lie inside set or not lie inside set. It means that suppose if I am telling x as a even number, then inside bucket I have 2, 4 or something like this, or outside the bucket where I am clearly seeing that what kind of quantity outside the bucket. So somehow definition is classifying quantity, quantity or things very, very much precisely. And whenever you are stating definition, then I have told you that please use if and only if, and in that way things become more precise. Or imprecise definition create lot of problem, and you are able to see that lot of I can tell fudgy papers. People are not careful with respect to definition, and due to that a lot of wrong things propagated inside the literature. Now let us come to the role of proof. So now what is role of proof? Proof are essential in mathematical reasoning because they demonstrate that conclusion are true or not. So I have a statement. Statement can be true or false. Now I have to give guarantee that under which condition a statement is true. And if we are able to do so, the method using which we are doing that is called the proof. And now most of you may means argue on this, that okay, I have some phenomena, so I will take enough number of example, and after that I will test that phenomena will work or not. If that will work for all input, then we are telling that okay, whatever proposition or whatever statement we are telling, that is true. But that is not the good way in mathematics, because mathematics is telling that something is either precisely true or precisely false. So you have to give guarantee that for all case, whatever things that is true, that remains true. False, if at one case something is false, it means that categorized as a false. So by doing enough number of checking, I cannot make any conclusion. And for that I have taken this example. Again, this example I have taken from the mathematics, but from control theory also you can able to take. I will tell you what kind of example, same kind of example existing in control theory. So basically, suppose this is number x square minus 3x 43, and x is some kind of positive integer, and after that we are telling that is a prime number. So now you can vary x from 1 to 42, and you are able to get everywhere that is prime number. But you can see that x equal to 43, what happens? Suddenly I have whatever value which will come, that is not a prime number. So basically, if you do manipulation, so basically I have 41.43. So basically that is not a prime number. So at least one condition means that is work for all example from 1 to 42, 44 to whatever prime number, whatever integer you can take, this relation will valid. But this is false at one case. So if you are doing checking, it might possible you will miss some kind of point where some result will not valid. So checking is not reliable way to tell that something is true, and due to that reason proof is very, very much essential. Now let us take one example from control system. So what happens that all of you might be knowing that x dot equal to ax, and suppose that this is linear system, and I am assuming that eigenvalue a of the matrix, if that is negative, then we are telling that x tending towards 0 as t tending towards infinity. So all are aware that it means that if system matrix is Hurwitz, then system is stable. But now what you can do, you can make system matrix A as a function of time. It is possible to show that in several examples it will work, that even it is time varying. At that situation, whatever eigenvalue calculation you are going to do, and it is possible to show that it's negative, but system become unstable. So means if you just suppose you have some system x dot equal to 80 into x, and you start checking, you are calculating eigenvalue each and every moment, and several cases you are finding eigenvalue is negative, and you are concluding system is stable. but it is possible to show that there exists some kind of counter example. So in that counter example, people has shown that even if AT, some matrix, eigenvalue of matrix is negative, but system is unstable. I haven't forget to collect that example here, but means in Slotin book you are able to see that kind of example, or lot of control book you are able to see that example. So let us again recall. So because several times I am recalling, because means this is not as usual lecture. This is lecture of logic, and logic is somehow little bit complicated. So recap again. Mathematics is concerned with the formation of theory. So we are talking about general theory, and that theory, what we have seen that we are making various axioms, and we are accepting that axioms. So basically that is nothing but collection of all the true statement. Whatever axioms I am assuming, that all axioms should be true, then only I can able to form some theory. So basically mathematics is concerned with the formation of theory with described pattern or relationship among the quantities and structure, and this use the deductive reasoning. So I have already told you that what is meaning of deductive reasoning. First, we are collecting several true statements, and based on some kind of logic, I am going to draw the conclusion, and that is nothing but the deductive reasoning. And proof is somehow demonstrate that whatever new theory now we are going to formulate, that is true or not true. And basically using proof, we are give guarantee to that. So now let us try to come what we have found that during the mathematical statement that may be true or false. So those kind of mathematical statement which is true, that is called proposition. So basically what happens that if, and sometimes people are using proposition and statement in somehow same fashion, but proposition, whatever I am going to talk and whatever control theory is going to talk, they are telling that proposition means collection of true statement. So but if something is true or false, then you can tell a statement and you can just collect out of true statement from there, that is called the proposition. But you can see that other statement what time it is, so I cannot able to tell that is true or false, because if at this time I do not know what is time now, I have just check that is around 11:30. So suppose I am telling 11:30, so that is true at this moment, but after some time this is not true. So in this way I cannot give guarantee. So whenever we are talking about proposition, then we are exactly able to tell that something is true or not. So in this way we are defining the proposition, and means a proposition is major importance is called theorem. So means whenever I am making some kind of a statement, and if that statement has very much important, then we are telling that as a theorem. So you may have seen that means KVL or KCL, Kirchhoff's voltage law, Kirchhoff's current law. So those are some kind of means collection of statement you can tell, and we are accepting that statement or proving that acceptance means statement. So that is nothing but the theorem. And so means what is difference between theorem and definition? So somehow definition is describing the word or mathematical object, and theorem tells us the relationship between different object. And here means those object, we are assuming that those object and properties well defined, then only we are talking about the theorem. So here you can see that one example I have taken, that if f is an even function, then df by dx is an odd function. So here you can see that this is theorem, and what I am telling that I'm not worrying that how to define even number, how to define odd number, or how to define df by dx. So all are the definition. So even number is definition, odd number is definition, df by dx is definition. But whatever things I have written, that is as it means that is theorem, because this is somehow one can prove that this is always true if f is a even number, then automatically dot by dx is a odd number. And similarly, now you can see that I have written lot of theorem. So f is even so first theorem we have already seen, second theorem, and third theorem. But one thing, several times we are assuming that we haven't understood the theorem. For particularly due to that reason, I have selected third theorem. So you can see that by one reading, you are not able to understand the theorem. Why? Because you do not know how to define kernel, how to define IM, or how to define dimension, or these kind of quantity. So, but even if you are not able to understand the theorem, but at least you can see the structure. Always I am writing if and then, if and then. So everywhere I have if and then, if and then. So at least I can see the structure. So now you can see that inside literature, we may have seen that I have proposition, lemma, claim, or corollary. Lot of things is written. So what is meaning of theorem? So theorem is somehow I have some kind of statement or proposition of more importance, and we are proving that that is true. And how basically we are writing theorem? We are writing if and then, and all kind of means either you can see proposition, lemma, claim, or corollary, all are written like this. But you can see that theorem is similar to axioms. But what is difference between axioms and theorem? Axioms we are accepting as it is and we are not proving, but theorem we have to give some kind of proof, and proving is one of, again, difficult quantity. So basically axioms we are accepting as a truth. Theorem, basically after that theorem I am again proving theorem. And basically now let us come to the lemma. So basically lemma is nothing but a small theorems. So suppose we have to prove some big theorem, then we are stating the lemma to prove in order to support the big theorem. So basically I have some big theorem, so I am splitting that proof of big theorem using a small sub theorem, and that is called the lemma. And corollary means there is no need to prove the corollary. Actually, if you prove theorem, then consequence of that automatically whatever new theorem comes, that is called corollary. And after that you can see that proposition or claim. So proposition, claim, or theorem, all are actually sometimes people are writing claim, sometimes people are writing proposition, sometimes people are writing theorem. So that is the difference. So major importance, so proposition of major importance is called theorem. And in order to prove big theorem, I need a small. I am splitting the whole proof into a small theorem, that is called lemma. And whatever the quite consequence of some theorem, that is called corollary. So in this way we are making difference between proposition, lemma, claim, or claim and proposition or theorem, all are same. So now let us come to the logical connectives, because this is very important. And why basically we are using these connectives? Somehow using connectives, we are now talking about another proposition, different proposition. And here I have already told you that whenever I am talking about proposition means I am talking about true statement. So here you can see that I have come up with the definition of stability. I have just bring stability definition here in order to show that how basically connectives is important for our purpose. So suppose that I have stated the definition of stability. So I have selected output ball, and corresponding to output ball, we are telling there exists input ball, and here limit point is x equal to 0. So what I am telling that somehow system is stable across x equal to 0 if for every epsilon, means every output ball, there exists some kind of input ball. And so for each means for all, and there exists is called inverted E. I have already told you that. Now suppose that I have to talk about the instability. So how to tell that something is unstable? So I will use this proposition, and that is called negation. So if I will put negation here, then that is the definition of instability. Again, I will tell you that how to manipulate this expression, because manipulation of this is not so easy. So if I have time, then I will tell you. Now another connectives is conjunction and disjunction. So that is same like and or. So basically, whenever we have complicated expression, then we are using conjunction and disjunction, that is represented as a or in order to simplify the expression. Now let us come here, that is very important part, that is conditional or biconditional statement. So what we have seen that whenever we are proving or whenever we are writing some means some theorem, then at that time in theorem I have a structure like if and then. If you see any theorem and higher mathematics, people are writing like this. In pre-calculus, we are writing that if two lines in a plane have same slope, then the line are parallel, like this. So always we are writing like this. So first we have to understand the definition of if and then. So if and then is called conditional statement, and so we are telling that P implies Q. So P is called antecedent and Q is called consequent, and we are telling that P and Q is true if and only if P is false or Q is true. So you can see from here, then that become more transparent. So what I have formed one table that is called truth table, and truth table, so I have P. So suppose P is true and Q is true, then P implies Q is true, and P is false and Q is true, so again that is true. And if P is true and Q is false, then that is false, and if both are false, then that is also true. So in logic we are believing on this. We are again, this is definition. So whenever we are giving definition, we are not telling that definition means we are not checking the definition. We are just believing on that. Suppose if your father is given your name as Ramesh, we are believing that my name is Ramesh. We are not checking why they have given my name or something. That is different things. So same with the definition also. So you can see here what is difficulty here in this definition. Whenever we are telling that P implies Q is true, then I cannot able to make sure the P is true or Q is true, because you can see that in second case, second row, if P is false and Q is true, again I have P implies Q is true. So by seeing in result, I cannot able to give guarantee that P is true or Q is true. You can see in fourth case that if P implies Q is true, then it might possible P and Q both are false also. So due to that reason, I have to select most proper quantity from here. And one of the most proper quantity, what we have seen that if we have observed here, if P is true and P implies Q is true, then Q is always true. So the first line you can see that if P is true and P implies Q is true, then only I can tell that, give guarantee that Q is true, and all proof is basically based on that. And this rule has some standard name that is called modulus ponens. And due to that reason I have written, and I will give you one example to understand this table. What we are telling that, suppose your friend tell you that if the concert is sold out, I will take you for selling. And suppose that it might possible that concert is not sell out, and still your friend is kind enough and he will tell you that okay, let us come for the selling. So that is due to that reason this kind of logic comes into picture. So what happens, you can see that concert is not sell. So first statement is false, and after that means they are telling that okay, let us go for the selling. So somehow we are, even if first is false but second is true, then we are telling that all consequence P implies Q is true. And in this way we are making the table. So means due to lack of time I am going a little bit fast. Now you can see that here whenever we are talking about the P implies Q conditional statement, so we have two different kind of things, that is converse. P implies Q, also tell Q implies P, and after that contrapositive of this P implies Q, you can put not operator. So that is called contrapositive. Converse means P implies Q is Q implies P. Now let us try to see that is there exists some kind of relation between P implies Q and their converse and contrapositive or not. So for that I have taken a very simple example, and what I am telling that if pi is an integer, then 14 is even, and from that table we know that 14 is even integer, and we know that pi is an integer, but we know that pi is not an integer, so this is false, because when first p is true and q is false, then finally we'll end up to the false statement. And now try to see the contrapositive. So first I have to see that if 14 is even, so negation of this is 40 is not even, and negation of pi is the pi is not an integer. So now you can see that if 14 is not even, so somehow what I am telling that 14 is not even, then pi is not an integer. So somehow I am checking that 14 is even, so this is false, and pi is not assumption, this become true. So false and true, that become true. Due to that reason I have written like this. And after that, similarly I have written second statement, and you can see here that 1 plus 1 equal to 2, and then root 10 is greater than 3. So converse statement of this is, I have written like this: root 10 greater than 3, then 1 plus 1 equal to 2. So that is converse, and you can see that first statement is true because 1 plus 1 equal to 2, and so true and true land up to the true. But here converse is also true, and contrapositive, you can see that contrapositive of this, I have to do negation. So negation of root 10 greater than 3 is means root 10 is not greater than 3, then 1 plus 1 is not greater than 2. So both are false. Again we'll end up to the true statement by seeing the table. So what we have observed in these two examples, that you can see that in first example, whatever p implies q. So if pi is an integer, then 14 is an even, so that is true statement, and contrapositive is also true. First is true, then that is contrapositive is also true. But in case of converse, you can see that even first statement is true, but some case converse is false, some case converse become true. So there is we are telling that converse and these things two are not the same, but contrapositive, p implies q, and negation of q implies negation of p, both are same. So due to that reason we have another method of proof, that is called proof based on contraposition. And those who are familiar with proof, they may have seen that sometimes whenever we are proving p implies q, so and if that is not difficult to prove, then we are assuming that first not q is true, and based on that we are proving that not p, and finally using this statement we are telling that p implies q is p implies q is true. In that way we are basically proving. So observation I have already discussed, that p implies q is equivalent to the contrapositive, but p implies q is not equivalent to the converse of this. So what you can do, you can go to your home and try to again read this slide very much carefully, because due to lack of time I am going little bit fast. But if you see the check from the table, because I have written almost everything, because this is subject of logic, so if you miss something, then you are going to give some kind of blunder. Due to that reason I have written a lot of things inside this slide, so try to read again. Now you can try to see the bidirectional statement. So what happens in conditional statement, we are talking about p implies q, so we are only moving in one direction, but bidirection we are moving in both directions. So we are telling that p bidirectional to q, so that is same as p implies q, and this is conjunction q implies p. So if I have some bidirectional statement, we have to prove in both way. And again if you see the table, then table is little bit different from p implies q, because we have to move in both direction. Due to that reason, true equal to true, and false equal to true. And I have already told you when I have started this course, that this lecture, that whenever we are making any definition, at that time we are always using if and only if. So somehow I am using the bidirectional connective whenever we are making the definition, and whatever table we are understanding, so that is the definition of this table. Now let us try to see this slide is again important, because if you try to read some literature in control theory, most of them they are telling sufficient condition, necessary and sufficient condition, and people become very much confused with this. So whenever I am writing p implies q, so that is translated in English like this: if p then q, p implies q, P is sufficient for Q, P only if Q, Q if P, and I have already given one example. So in this way we are interpreting. And similarly, if I am writing like this, so I have same kind of, so P if and only if Q, P if but not only in Q, P is equivalent to Q, P is necessary and sufficient to Q. So in this way we are translating this. Now let us, I have written most important remark, because in literature most of time I have already told you that we are talking about necessary condition, necessary and sufficient condition, these kind of things. So try to understand what is meaning of necessary condition, what is meaning of sufficient condition. I will again bring one example from the control theory. So a necessary condition is the condition that must be present for an event to occur. So if necessary condition is not present, then we are hoping that events is not going to occur. A sufficient condition is the condition or set of condition that will produce the events. So using sufficient condition, we are giving guarantee, okay, if these conditions are satisfied, then some events is going to occur. But we are not telling, even if some case, even if this condition is not satisfied, then also means events is going to occur. So here, due to that reason, we are just telling this is sufficient to create some events, but I cannot tell that if this condition is not present, then what is going to happen. But in first case, in necessary condition, we have to give means all necessary condition to occurrence of the events. So if one of the necessary condition is not satisfied, then events is not going to occur. So a necessary condition must be there, but it alone does not provide sufficient cause for the occurrence of the event. Only the sufficient ground can do this. In other words, all the necessary element must be present there. And I will again take the example of Lyapunov stability. So several necessary conditions that taken together constitute a sufficient condition. So and so individually each and every condition are necessary, but jointly that is called sufficient. And those who are familiar with the Lyapunov stability, they know, they must be well aware that suppose some system is stable, even if we are not able to form Lyapunov function for that particular system. So if we are unable to find Lyapunov function for some system, then we are not able to claim that that system is stable and unstable. But if we are able to find Lyapunov function, and if this condition is satisfied, then we are able to give guarantee that system is stable. So that is the meaning. So somehow, if you see all three conditions, so V equal to 0 at 0 is the necessary condition, Vx greater than 0 when D is not present inside 0 set, this is necessary condition, V dot x less than equal to 0 is the necessary condition for the occurrence of the events. So, and these all mixed together is going to make some kind of sufficient condition for the stability. So you can see that three necessary conditions come together, and after that they are going to generate some kind of sufficient condition for the stability. So in this way, we are so whenever you are proving, whenever you are means proposing some new theorem, there exist several necessary conditions, but it might possible in result of that collection of all necessary condition may produce just sufficient condition only. And I will give you one more example. So a number being divisible by 4 is the sufficient condition, because if something is means that is not necessary. If something is divisible by 4, then it is obviously even. But if that is not means divisible by 4, then we cannot make any kind of things, any kind of claim. Due to that reason, we are telling that this is sufficient condition. But divisible by 2 is both necessary and sufficient condition. So if something is not divisible by 2, then clearly I can tell that is the odd number, and due to that reason, that is called means necessary and sufficient condition. So I hope that using this slide you are able to understand that now what is meaning of necessary condition, what is meaning of sufficient condition, what is meaning of necessary and sufficient condition. Now let us try to come quantifiers. And quantifier, I hope that I have no at 5 or 10 minutes just, so I'm again little bit go fastly. So what is meaning of quantifier? What happens that I have some kind of open statement. What is meaning of open statement? Suppose I am telling x greater than equal to 3. So I do not know the truth value of this statement. Why? Because if x is 4, then this statement is true. But x is 2, then this statement becomes false. Due to that reason, whenever some variable comes into picture, then at that time we have to define the universe. Universe means I am telling that, okay, if x greater than equal to 4, then x greater than equal to 3. So I have defined the universe. So whatever things we are talking, that is only valid in some limited universe. And due to that reason, this quantifier, again, I have two different kind of quantifier, that is called existential quantifier. So something is only true for some special case and something is true for all. So meaning of existential quantifier, I have already used this kind of quantifier when I am defining the limit or whenever I am defining the means stability. So what we are telling that px, open sentence px, and this sentence whenever we are adding the quantifier, so there exists x is the quantifier. So one can read like this, and here you can see that I am telling that x greater than 3, there exists x. So this is true statement. Why this is true statement? I can give some x when this statement is true. There exists x when x equal to 0. There exists x when x square equal to -1. And if you see the dynamical system, then again that is also means that is just governed by existential condition. Why? Because we are telling that input and output data set should be related to the real number. It means that my universe, whenever we are defining dynamical system, so input and output should be real number. So again, that is the existential quantifier. And I will skip this slide. So next slide is the universal quantifier. So I'm telling that is true for all value, means entire universe. And we are representing that by inverted A. So you can see here that I have given selected certain example. So for all x plus 2 is greater than x is true. And similarly, I can tell that this is always true. So for all x greater than 3 is false, because some x is not possible that is greater than 3, something is not greater than 3. So in this way, we are using the universal quantifier. So basically, I have what we have seen. I have 3 different means at 5 different kind of connectives. So I have a not connective, and connective, or so and or we are telling conjunction or disjunction, and after that we are telling that I have conditional statement P implies, so that is also connective because connecting two statement, and after that bidirectional connective. And quantifier, I have 2 different kind of quantifier. One people are also telling that is means there exist unique. So but I have most of time we have 2 connect means quantifier, that is for every or there exist. So whenever you are seeing this kind of word, for all, for every, for each, then that is called universal quantifier. Whenever we are seeing this kind of word, this means we are talking about the existential quantifier. Sometimes these kind of quantifier is hidden inside the word. So please try to find means the quantifier. Suppose that polynomial function are continuous. It means that we are talking all polynomial function are continuous. It means that here I am using for all. So now symbolization of sentence means whenever we are telling that all P are Q, then we are symbolized like this. And whenever we are telling that some Px are Q, then we are symbolizing like this. So the symbolization is important, because whatever we have seen that means whenever we are writing stability, so for every delta there exists, or like that we are writing. So several times we are not using word, we are using this kind of symbolization. So you have to become familiar with this kind of means this kind of symbolization also. And 2 statement is called equivalent statement if both have the same truth value. And now what I'm telling that here I have already told you that these 2 statement is equivalent, because Px implies Q for all x is equivalent to their contrapositive, because we have already seen. So these 2 statement is equivalent, and these 2 statement is again equivalent, means if you put negation, for all x ax, it is possible to show that there exists x and negation of ax, and this is required because what we have seen that whenever we are defining stability at that time, we have to define instability also. So if something is unstable means that is not stable. So at that time we have to manipulate the sentence. So in order to manipulate that sentence, we have to understood these two theorem. So whenever we are putting negation for all x, then that is converted into there exists or not symbol across this sentence. And similarly, there exists is converted into for all x and with the negation. And this is again means I have taken one symbol. So please do practice at your home. And this is there exists unique. So sometimes we are telling that there exists some kind of unique element. So suppose that if I'm telling that x square equal to 4 is true for all x greater than x greater than 0. So at that time there exists only one unique quantity. So at that time I can use this kind of quantifier, and that is called means there exists a unique. So till now what we have seen that means in order to develop any theory, I have told you that first I have to form the axioms. And how basically we are forming the axioms? Using, we are putting all kind of quantity inside this set. And due to that reason, now I am going to conclude this lecture. So actually, suppose I have to form dynamical system. So I am putting input, I am putting output, I am putting a state variable inside one set. So somehow set is nothing but unordered collection of the object. But you all are knowing that this world is not unordered. This is somehow ordered world. So somehow I have to define some kind of ordered quantity. So how to move from unordered to ordered? So in order to move from unordered quantity to ordered quantity, what we are going to do, we are going to define some another mathematical notion that is called Cartesian product. And you all are knowing that when set I have set A and set B, then how to define Cartesian, and we are defining like this. And here I have two different kind of quantity that is called relation, and another thing is function. So function means if you see the y, so corresponding to y, corresponding to output y, you are able to find this kind of relation. Means we are telling that output is always unique corresponding to some input. So if you give some specific input, you are always going to get some kind of a specific output or unique output, and that is not a relation, that is a function. And due to that reason, we are telling that any machine, whatever machine you are going to develop, that satisfy the property of function. And due to that reason, means suppose that now you can see that I have taken one example of pendulum system. So this is the mathematical model. I am not going to explain that how basically I am come up with this mathematical model. And we are representing this system. We are putting inside x theta1 and theta2, and after that we are going to represent like this. Here what I am telling that x belongs to Rn, means that is the generalization. Means suppose second order system, then x belongs to R2. So if I have just first order system, x belongs to R, one real number. But suppose if I have n number of state variable or n number of input, n number of output, at that time I am going to put this kind of n, means R cross Cartesian product, R Cartesian product, R up to n time. So due to that reason, we are telling that x belongs to Rn. And I have already told you that whenever we are making relation between input and output, in order to make the uniqueness, always what I have to do, I have to define function. So machine is function. Due to that reason, this is function which is mapping from Rn to Rn. So this system is called autonomous system because no forcing function is involved here. Another is called non-autonomous system. Non-autonomous system, time is explicitly present. In first autonomous system, time is present but implicit. So x is changing with respect to time, and after that we are talking about rate of change. So somehow we are defining quantity with the some kind of variable. So position vector, and this is x dot is the velocity vector. So using position or vector, so in axiomatic field or in system theory, we are telling that as a field. So using position vector and their rate of change, we are defining some quantity with help of the function. If time is explicitly present, then we are defining non-autonomous system. And again, you can see that now function R plus, it means that we are just talking about the positive time order always matter. Due to that reason, I have used notion of Cartesian product like this. And force system can be defined like this. Again, using the you all are knowing about the composite system. So using composition, I can define the means I can define only two class, because here you can see that in place of u, if I substitute some function that is just function of x, then again this system is converted into autonomous system. If that is, it means that if we design some kind of control which is just depending on the state variable, then course system is converted into autonomous system. And if control is also explicitly depending on the time, then system is converted into non-autonomous system. So with help of composition, proper composition function, we are defining like this. Again, I have already told you that I am talking about limit, and somehow we know that left hand limit, right hand limit, and limit at the point, then function is continuous. But here now story is different, because continuous function is going to lie in higher dimensional space. So somehow I have to define some quantity which is exactly like the absolute value, and that is called norm. So basically, in place of absolute value, I am going to substitute with some kind of distance kind of notion that is called norm. And again, you can see that definition remains like same. First, you have to select output side, and if input side is also lie inside delta, then we are telling that function is continuous. And after that, uniformly continuous. Then in case of uniformly continuous, you can see that delta is function of x0, means we are talking means continuity across some point, and here that is independent of that in that way. And so norm, so let us try to understand the structure. So first we have defined the set. So set is an ordered collection. After that, from an ordered, we have defined the ordered using Cartesian product. So now after defining ordered, I have take those kind of relation which is provide the unique output, that is called function. So we have involved function, and once I define function, then I have to define some kind of operation, and that is called nothing but the vector space. Whatever means, I am not going to means talk about algebraic structure. Again, we have to define algebraic structure, and inside algebraic structure, I have to define some kind of distance kind of notion that is called norm. So norm is nothing but some kind of distance kind of notion. So if you understood these all quantity, then you are only able to understand about the system. And now again, come up to the definition. In last, you can come up to the definition of stability. And I hope that you are already able to understand this. You are already able to understand the limit. So you are able to understand the definition of asymptotic. So in this way, so briefly, this is the story. And another now next part is about the proof. So so now I am going to stop here. So I will talk to Bipin. Bipin, Dr. Bipin, are you able to? So should I conclude, or I have 10 minutes?
Sir, if it is possible, then you conclude, or you can 5 minutes, sir.
Okay, 5 minutes I will conclude.
Yes, sir. Yes, sir. Okay. Thank you, sir.
So what happens till I know till this time what we have seen, that I know how basically we are come up with the theorems. So I have axioms. After axioms, what happens? I have give some kind of definition of a structure, and after that I am connecting several structure together, such that we will come to the relevant quantity that is called theorem, lemma, corollary, the claim, or something. And after that, now somehow I have to prove that whatever proposition or whatever theorem that is true. If that is false at any one instant, then that is I cannot accept that as a theorem, lemma, proposition, corollary, etc. And due to that reason, means way of checking, I cannot prove anything. So I have to go with logical way. And believe on me, I have just 5 different methods to prove anything. So means due to that reason, I am telling that grammar of mathematics, this whatever till now I have told, that is the grammar of mathematics basically. So grammar of mathematics is basically based on axioms, definitions, theorems, and after that I have connectives. I have already told you that not connectives and connectives, or connectives means conjunction, disjunction, and after that I have bidirectional, and after that conditional means P implies Q, and after that I have quantifier for all, or there exist unique. So based on this structure and using the notion of set, Cartesian product, function, and if I connect or put everything inside some bucket, then we are able to understand the theory. Now, one part of grammar is related to the proof. So how to do the proof? And actually, whatever things we have learned till now, proof is basically based on that experience only. So, and what we have seen, that structure of theorem is if and then. So somehow P implies Q. So I have to see very carefully when P implies Q is true. So based on that only we are creating the proof. So this is the guidelines. So only I have 4 guidelines to do proof. And tautology means that if something is true always, then that is called tautology. So based on just 4 strategy, one can prove. And I have 5 different methods of proof. So quickly I will tell you. First proof is called direct proof. So what we are telling that if P proposition means whatever we are writing if, so whatever axioms is true, and if P implies Q is true, then there, and if I will define the conjunction, then implies that Q. So if P is true, P implies Q is true, then I can tell that Q is also true. We have already seen from the table. So proof is based on this methodology only. Another proof is based on contraposition. What we have seen that P implies Q is exactly equivalent to not Q implies not P. So second way of proof is called indirect proof. And sometimes it is very difficult to directly prove. So at that time we are assuming not Q equal to not P and prove that statement. So that is the indirect way. And another way is contradiction. We are creating some kind of contradiction. And why this method will work? Because we know that I have just 2 things. If I have either, if I am writing some theorem that is either true or false, because that is mathematical statement. So that has just 2 values, either true or false. So if somehow I am assuming something as a false, and if that is not false, or something as a P as a true, and somehow we create that P is false, then automatically proof happens. And this is the method of the contradiction. And so somehow we are creating some kind of contradiction, and somehow contradiction method means proof by contradiction is more useful in several situations, but very, very tricky, because we have to create some kind of in between statement where Q will come, and Q we are not knowing. But 2 way of proof, direct proof or indirect contraposition based proof or direct proof, both are means straightforward proof. But proof based on contradiction required little bit experience. And 2 other method of proof is called proof by counterexample. So whenever some theory is there, you can just create one counterexample, then whole theory will collapse. So that's the way of proof. So proof by the counterexample. And last way of proof is proof by mathematical induction. You are also you are knowing that I am assuming that something is true at k equal to 1. After that, we are assuming something is true at k equal to n, and we are checking that by assuming k equal to 1, k equal to n. I am checking that something is true at k equal to n plus 1 or not. So that is the way of proof of any sentence. So now let us come to the conclusion. So what we have seen that I try to teach grammar of mathematics, and grammar because somehow I have physical object and we are representing physical object with abstract object, and abstract object is coming from mathematics. And suppose if you are not knowing the grammar of some language, we all are agree that mathematics is nothing but some kind of language to represent some quantity. And if you are not knowing the language of some suppose you want to know English or Hindi, so you have to know the grammar of that. And due to that reason, means this logic or proof are very essential, very much essential to know, because that is the grammar of mathematics. So you are expressing your physical system using some set of mathematical equation. And due to that reason, I hope that this lecture is relevant. Lecture is a little bit fast because means I try to sum up everything. And means another most important point involved here, that in order to understand, no one can teach you logic. You have to teach by yourself. So what you can do now, you can go with one by one slide and try to understand each and every point. So with this remark, I am going to conclude my class. So thank you very much. Thank you very much, Bipin.
Thank you, sir. Thank you, sir. Thanks a lot for sharing your great knowledge with us. And also you have discussed a lot of things from the very basic, from 10+2 That is the standard where we just educate, and up to the recent advancement in the knowledge from that means in research, or we can do the other work in the field of control system, and also the stability from the proposition, definition, formation of different theories, and all the other things that are very much relevant to our problems. And I think our research scholars will very much benefited from this. So now I want to just open this session for queries and questions. So the participants, if you have any queries, then you can please ask.
Any question is welcome, even if that is because now you are able to understand the means it is very difficult to understand a small thing. So any question is welcome. I will share this slide.
Yeah, you can also write in chat box. Sir, one question is there.
Yeah, that is, I have seen that. What is difference between exams and postulate? So basically, if you believe on me, both are almost same. And why I am telling both are almost same? Because one is exams, maximum time we are using for mathematics. Postulate, whenever we are telling, then we are defining in terms of science, means physics, chemistry, or mathematics, or some physics, chemistry, biology. We are defining as a postulate. So basically, postulate it made possible that at some point we are unable to check because that is based on our experiment. So, and always experiment has a limitation. Experiment I am going to do. So that is true, but it might possible in future something will come into picture where things become false, then whole theory will collapse. But that is not with the axioms. In mathematics, axioms is consistent set, so that will never going to become false. But postulate may become true, may not become true. So postulate just we are believing, but if some kind of experiment, some new experiment come into picture, then what we are telling that whatever postulate, we are discarding all the postulate. And after that, there any impact of asymptotic stability feedback. Obviously, asymptotic stability is very, very important for the feedback. Why I am telling? Suppose you can take one example. Suppose you want to put some kind of satellite in Earth orbit, and due to some disturbance, if satellite is deviated, then you are you know that we are not able to gather proper information. Due to that reason, what we are telling that due to some unknown force, if satellite is deviated from that orbit, then finally after some time that will again converge to the our original one. So that is only possible if I will design my satellite or control of satellite in such a way such that it will again come to the original orbit. But what is meaning of stability? It means that okay, if some disturbance comes into picture, then that will not much deviate but remains in another orbit. So that is difference. Due to that reason, asymptotic stability is very, very much essential in the feedback design. Any other one?
Sir, I think presently not now any query. Okay. All are satisfied.
So one more important thing I am going to highlight. One book that is a transition to advanced mathematics. So using that book, that is free book, and very good book to understand logic and proof. So those who are really want to learn logic and proof, please see this book, A Transition to Advanced Mathematics. So I will share that book.
Excuse me, sir. Very good morning. This is Dr. Sunil from NIT University.
Okay.
Very related to this practical and theory.
One minute, please. Please repeat your question.
Sir, I want to know there is a lot of gap between practice and theory of control systems. So whatever advanced theories we are developing these days, those are very advanced. But when we go for real-time implementation, There is
No, actually, in order to answer this question, I will tell you two things. So actually, why we are learning new theory or advanced theory. So if you learn advanced theory, it is possible to simplify the existing design also, and it is able to get some good set of parameter if you are able to understand the higher dimension of theory or higher level of theory. Suppose PID controller, you can take example of PID controller. So if you just learn PID controller, then you are not able to understand how to select KP, KI or KD for some particular purpose. But if you learn higher mathematics or higher level of control theory, so using that higher level of control theory, now you are gaining insight much about the system, and at that time you are able to easily tune KP and KI on KD in more efficient way. So due to that reason, means people are telling that we have necessary to learn higher theory even if we are working on lower level. Now I have two different classes of system. One classes of system is called sophisticated system, very, very sophisticated, where failure is become very much dangerous. Suppose that you are flying with aeroplane and so hope that at certain moment your controller will not work. Then what happens? Means it might possible that means your whole flight will collapse, and after that if this kind of collapse happens to 10 times or 20 times, then people very much afraid to travel using aeroplane. So at that time you have to give guarantee. So at that time I cannot use some kind of simple controller, so we have to use sophisticated controller. Now we are talking about robotic doctor. We are again talking about another important thing. You know that means in war we are using some sophisticated instrumentation, and there at there I cannot use simple PID controller. I have to use advanced controllers. So depending on the problem, and whatever problem, most of problem which is in our life, that is very, very simple. Due to that reason, simple controller is very much working there and very efficiently working there. But if you are talking about critical problems, and now it is age of network control system, and critical things come a lot. Due to that reason, we have to learn higher level of control theory. Since we are academician, so we are believing that if you learn higher level of something, then a smaller thing or lower level things become obvious to you, and you are able to think more about the lower level. Due to that reason, I think that higher level things is required, and obviously for sophisticated system, I cannot work with the lower order theory, and most of us are not working with the aerospace system, missile systems, or biological system. Due to that reason, we are believing that PID controller is enough. But if you work on that direction, suppose you have to develop some kind of strategy to cure the cancer, at that time I cannot apply some kind of device which is based on PID controller. So due to that reason, that is just this is the explanation to your question. But so you have to become very much careful that what is your application and what kind of theory you are going to use. And one question I found, that lemma and theorem. Actually, theorem, sometimes what happens, that theorem is become very much bigger. So in order to make theorem smaller, what we are telling, that suppose you are writing some C programming. So how basically we are writing C programming? I can write in two different ways. I can define one function, inside one function I will write all program. Another way, I can write different function. Different function has some specific behavior, and after that I will call all function. So basically that is the difference between lemma and theorem. Somehow lemma is the smaller part of the theorem, so that is same property like theorem, but that is a smaller for some important context. So lemma is also a theorem, but that is a smaller one. And if you write one paper, so suppose that in most of paper only I have one excellent result. So what you can do, first you can write several lemma that create the small events, and after that you can just connect all events inside the theorem such that you can generate the theorem. And after that servo signal is not considered in ideal input. Oh, okay. Actually, means sometime what happens, I have two classes of system. Some classes of system is called autonomous system, some class of system is called force system. So basically what happens, that whenever I have some kind of forcing function, either we are telling that means forcing function I have to design, so I can select in any way. So either I can assume that forcing function is a function of time or function of state. So due to that reason, suppose that if you are assuming that forcing function is just function of state, then my force system x dot equal to fx again converted to the autonomous system. And if that is function of time and state, then that is converted to non-autonomous system. So I have two different kind of things, analysis and synthesis. So now you can see that if I know the property of x dot equal to fx, then I can understood everything about the autonomous system. Similarly, if I know the property of x dot equal to ftx, then I can understood about the non-autonomous system. Now, whenever you have force system, then you can select your input and try to fall inside either autonomous class or non-autonomous class. So there is no need to develop several separate theory for the force system. But suppose that now forcing function is unknown. Suppose you have some disturbance or something is coming. So at that time, you have to also consider the force system. And for that, input to state stability is very much relevant. We are telling that if input is known, then I can either convert system into autonomous and non-autonomous. But if input is not known to me, then I cannot convert force system into autonomous and non-autonomous. Due to that reason, separate theory for non-autonomous system is required. Means force system is required, and that is governed by input to state stability. At that time, I am not able to maintain the equilibrium point. Due to that reason, I cannot, because in presence of disturbance, I cannot able to define the equilibrium point. How basically we are defining equilibrium point? By axiomatic way, we are telling that where rate of change Cj is x dot equal to 0. So if I have unknown quantity, I cannot able to know where is my equilibrium point. So I cannot able to talk stability in sense of Lyapunov, because whatever Lyapunov sense, they are talking stability with respect to equilibrium point. Now I do not know equilibrium point. At that time, I have to involve some kind of servo signal or some kind of unknown signal to analyze the stability of whole closed loop system. And okay, so now so now I have to move to next session. Any other question? So if now you have questions, I have already written my email ID inside this slide. So please just email to me. And if question not become clear, then I will give my email ID or phone number. Then you can talk.
Thank you, sir.
So
I think all the queries has been satisfied, sir. And
okay.
We are expecting that your lecture has very significant impact on every participant. So we are very much thankful, sir, for sparing your valuable time with us and sharing your great knowledge. Thanks a lot. Thank you, sir.
Thank you very much. So now I am going to exit.
Yes, sir. Thank you, sir.
Thank you.
So, dear participants, now we are moving into next session. So the next session, in that session, we will discuss about the model control concept. And in that session, Dr. Soham Chakravarti from IIT Roorkee, he has joined our session, and he will deliver the talk. So just I am giving the brief about him. Dr. Soham Chakravarti is serving the role of assistant professor in electrical engineering department, Indian Institute of Technology, Roorkee. Prior to this, he has worked as a research associate in University of Kent, UK, and has been invited as visiting researcher in Lodz University of Technology, Poland, and as visiting associate professor in RMIT University, Australia. He had obtained his PhD degree in control system from Indian Institute of Technology, Bombay, India. He has been teaching nonlinear systems and robust control, sliding mode control and observation, modeling and simulation, digital electronics as part of his appointment in Indian Institute of Technology, Roorkee. He is also doing research in sliding mode control, multi-agent system, and learning-based control. Now with this, I invite Dr. Soham Chakravarti, sir. Please start, sir, please.
Yeah, hello everyone. So I just want to confirm if the slide is visible,
Yes, sir, it is visible.
because it is not coming as a feedback to my side. So I am not very sure about it.
No, it is visible, sir. It is visible. Model control.
Now I have done. I have made it full screen. So now, is there any problem with it?
I think no problem with us, sir.
Okay, fine.
Yeah. Thank you, sir.
Okay, thank you for giving me this opportunity to speak on some very basic concepts. Actually, I will try to cover, and most of us already know about the frequency domain approach to control system analysis and design. And what today I will try to discuss are the stepping stones into the modern control concept, where we are actually seeing system representation in time domain as it is, and trying to analyze it in the time domain, and as well as design controllers in the time domain itself. So that is what constitutes the modern control concepts. And I would like to thank my previous speaker, Dr. Shyam Kamal, and we were actually colleagues together when we did our research. And he has covered really a beautiful part of what we actually sometimes we fear this part, but he has tried to give us an understanding into that part in a very beautiful manner. The mathematical logic and its understanding is really very important, so that we can move ahead and work with these modern control concepts. Though I will not be using so much of definitions or so much of mathematical definitions like that. But when you are working on some concepts, some advanced topics, then that will be very useful. Vipin, is my video on?
Yes, sir. Yes, sir.
Is my video?
Yeah, yes, sir. You are clear. Your
No. My video. I haven't turned on my video, I think.
okay. Actually, it is not only PPT. Is just we are seeing the PPT only.
You are seeing only the PPT. Okay, no
Yes,
problem. Then I will turn off the video.
Okay, sir.
Just to save on the bandwidth. Okay.
Okay, sir.
Fine. Okay, fine. So let us move ahead. So I will try to move a bit quickly, because I've started a bit late and I wanted to cover something. So I hope you have a fair bit of understanding on this topic. So I will not be spending too much time on each of the topics, each of the individual topics. So let us move ahead and see. So what I will try to cover in this are these two parts. So I have broken it down in part 1 and part 2. So the first part, I will just show you some state space realizations and how they are, how we obtain a solution from them, considering continuous time, linear time invariant systems. And in the next part, I will study a bit more. We'll go into the analysis part. So we will analyze certain characteristics, structural characteristics of state space realizations, which I will call as SPR. So some structural characteristics of SPRs, which enable us to actually design controllers and observer. What is observer? We will also see. So controllers and observers for the SPRs. So let us dive into it straight away. So how does a SPR look like? So it is generally having this sort of a look. So what it is basically trying to say, we are having several variables defined whose first order differential equations we have with us. So this is the model of the system. So if you had considered the transfer function model, then there we were only seeing the output how it is related to the input. So we are only having these two variables, output and input. However, in state space representations, we are introducing several variables which are called the states. How many of those variables we are introducing, as is the order of the system. So we know what is the order of the system even from the transfer function. It is the order of the characteristic polynomial. So those many number of states we have to introduce in the system, and we would have a fair understanding of what is the evolution of those states. So this x dot, so x1 dot up to xn dot, we would know. So what x1 dot is, we have very good understanding of what x1 dot is, and so for all the xn. So like here it is, suppose it's a function, and normally it is a function of all these states. These are called the state variables. All these state variables as well as the input. You see that the output is not featuring here. So these state dynamics, which are first order differential equations. So these are
Sorry to interrupt you, sir. Sir, actually, slides are not moving. So
no, slide is not moving. This is the slide number 3.
Okay.
This is the slide number 3, right? Okay.
Okay.
Yeah.
Sir.
So these dynamics is dependent on the state variables and the input variables only. And how the output gets related to the input? The output is basically having an algebraic relationship to the states as well as the inputs, sometimes, not always. So normally this input doesn't feature directly in the output equation, but output is basically getting influenced by input. So how does it happen? It happens through these state variables. So the input influences the state variables. They are dynamic in nature, so they are always changing themselves over time, and that change is getting reflected at the output in some algebraic relationship with those state variables. So if you consider a simple linear time invariant system, we'll see it in the next slide. You will get a more clear understanding of this. Now, what are some features of this state space representation? You can go through these points. I hope you have already looked at it. So the most prominent feature is that it represents all classes of systems. So there is no restriction, like in transfer function representation. We have to restrict ourselves to linear time invariant cases. So there is no restriction here. Also, it is not restricted to zero initial conditions as in transfer functions. We have the internal state dynamics revealed. So that is not happening in the transfer function.
Sir, sorry for interrupting. Sir, please click on that slide. Actually, we are seeing only first slide, modern control concept part 1. So please click on that slide so that will be visible to us also.
So I am moving the slides. Is it not moving?
No, sir. It is not moving. We are seeing only first slide.
Okay, I understand. I understand the difficulty. Let me redo it. So I stop presenting. Now are the slides moving?
Yes, sir. Now it is moving. Now okay. Okay, sir.
Okay, good. So I was actually on this slide, and what I was talking about the state dynamics and how the output is related to the states, and how the state dynamics are related to the states and the input. So this is where I was. Probably you already know this, so let us not waste time again repeating this. So that these are the features of the state space representation. And now here is the block diagram of the linear time invariant systems when represented in this SPR. And this is the form that it takes for a LTI system. We are very familiar with this form, x dot equals to ax plus bu and y equals to cx plus du. So what is happening actually here, you can understand that x dot being the time evolution of the states that is influenced by the states themselves through some operators, which is a matrix operator, and external force can also influence it. So it is getting influenced by its present position as well as external force. And this is causing evolution of the state variables. And whatever the state variables are, that is contributing to forming the output. So it is having a relationship in order to give you the output. D normally becomes 0 in most cases. If you have a strictly proper transfer function, then your D is basically 0. But if you have a proper transfer function where the numerator degree is equal to the denominator degree, then you will see that this D is non-zero and the control input directly influences the output. So a formal definition of state. So as we were looking at definitions, etc. in the previous presentation, so it is defined as the minimum information that is recorded at the initial time t0, which is needed together with the knowledge of the input for all times in order to predict the behavior of the output for all times. So we need some minimum set of information at the initial time. Based on that information, we will be able to predict the behavior of the output given a control input, given the knowledge of a control input. So that minimum set of information is defined as the state. Looking at this, you can very easily understand that how I am getting the output behavior through these state variables, right? And how I am getting these state variables, the evolution of the state variables are governed by this dynamics. So in order to solve for the xt at a particular instant, we would need knowledge of the initial values of this x1 to xn. If we have the knowledge, then this is already known. This f1 to fn is already known because this is a model, so we know this. So we have fixed these functions, but we need to know the initial conditions, initial values we need to know. If we know the initial values, we will be able to calculate, at least if not with an analytical solution, at least through a numerical solution, we will be able to calculate the x1t to xnt. And then we will be able to figure out what the output is. We will be able to predict the output behavior. And this input must also be known for all times. So you see that how the definition fits with the representation. Now the state space realizations can be derived from the system dynamics, from the differential equations of the system, the governing laws of the system. They can be derived from the block diagram representations of the system, as well as from transfer functions, which is only restricted to LTI systems, of course. But we'll look into the transfer, into some of the state space realizations getting derived from transfer functions. And the first one is called the phase variable form of the first companion form. And we look at a general transfer function, and from here we would try to develop the SPR. Now we to deal this in the phase variable form, what we do, we break it down into two different transfer functions. One which does not have any zero, like this one. This one does not have any zero, only the characteristic polynomial in the denominator, and another one which does not have any denominator, only the numerator polynomial. Now we first look at this particular ZS by US. So ZS is like an intermediate variable, you can understand. If we multiply these two equations, we get back this particular equation. So ZS is like an intermediate variable. So now if we look at here, this particular transfer function, from there you can get this particular differential equation. And now if you define z as x1 and then continue defining x2 as x1 dot, x3 as x2 dot, like this till xn equals to xn minus 1 dot, then after that what you will see that xn dot becomes basically dnz. Xn dot basically becomes dnz, and then you can express all these z, dz, etc. in terms of x1, x2, etc. because of your choice of this z equals to x1, and then further forming a further defining the other states in terms of the differentiation of the previous state. So then this z becomes your x1 basically, dz is x2, and this dn minus 1 z is xn, and you write it in terms of the state variables that you have defined. Then you get the entire ordinary differential equations, first order ordinary differential equations of governing the state dynamics, which is written here, and this z is x1. So in case there are no zero, this is the state space representation, and you can very easily understand that the A matrix will be like this, the B matrix will be like this, and the C matrix will be like this. And if we have the zeros, so if we have the zeros, then we have to consider further this particular equation. We have to consider further this particular equation. So from that equation we get y as a sum of all these different terms, all these different derivative orders of z. Now all these different derivative orders of z are what? The states that you have already defined. Z has been defined as x1, etc. dnz is xn dot, dn minus 1 z is xn. So dnz is xn dot. So you see b0 xn dot plus b1 xn, etc. Now xn dot we already know from the equation. So xn dot we put back. So this is xn dot. So we put xn dot back and we club the coefficients of each of the states, and we get this equation. So what equation changes here? The output equation changes when you include the zeros. The state dynamics does not change, only the output equation changes. So then what happens? Your total SPR looks like this, and you see the state A matrix and B matrix remains same, but the C matrix has changed. So in this way actually we can derive the first companion form. And next we look at the block diagram. So this is the block diagram of the first companion form. The same equations that we have derived, they are represented in a block diagram form using the integrators, gain blocks, and summers. And you can very easily read the block diagram by looking at these ABC matrices. Like you can see that, and this is x1 dot, because the output is x1, so the input is x1 dot, and x1 dot is equals to x2. X1 dot is equals to x2, and likewise all the other states are like that. But xn dot, what is xn dot? Xn dot is this u plus this entire signal, and this entire signal is basically a1 xn plus a2 xn minus 1 dot 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 plus an x1, and this is coming and with a negative sign. So these negative signs are also getting reflected here. And the output is basically all these b1 xn, b2 xn, etc. was there, and the b0 xn dot was there. So we take the xn, take the xn dot and pass it through b0 and add it to all these signals to get the y. This is one particular representation. We see another representation which is called the rectangular form. Here we manipulate the transfer function a bit differently, and we come to this particular equation. So we manipulate it in a certain way, and so you will get the slide, so you can look at it in your own time. So what we have got is basically we have got the output as a summation of this sort of signals like BIUS minus AIYS being passed through integrators. So 1 by S is like an integrator. So you see this particular signal has been passed through n number of integrators. This particular signal has been passed through only one integrator. So this particular signal will come and sit at the input of the last integrator. So this one. At the input of the last integrator, we are seeing B1US, B1U and A1Y. A1Y is coming through a minus sign. Now, the other signals will pass through so many number of integrators. So like you see, this one will pass through n number of integrators. So this one is BNU, BNU and minus ANYS, BNU minus ANYS. So this signal is passing through n number of integrators to come to the output. So in that manner, this block diagram has been drawn. And from this block diagram, now it is very easy to generate this set of state dynamic equations, and the output equation is this. You will check there, output equation is x1 plus b0u, and from then onwards we can write this x1 dot as x1 dot is x2, this is coming here, plus this equation plus this signal plus this signal, and plus this signal and plus this signal. So this is what is making the x1 dot. So this is basically the y. You see a1y. So a1y and y we have replaced. Since y is x1 plus b0u, y we have replaced here. So you can understand in the rectangular form what happens. The peculiarity is this, that the x1 state is influencing all the state dynamics. Okay, through these gains a1, a2, a3 like this. So you see the A matrix. This A1 to AN are sitting in the first column. In the first component form, they were sitting in the last row. Here, they move to the first column. And then the B becomes like this, and C is like this, and D is like D is B0. So, so this is the another form. And this particular form is very useful, which is a diagonal form. Here, what we do, here we break down the transfer function into partial fractions. And we can calculate these residuals of the partial fractions, and then what happens, we define the states like this. Each state xi is defined through this partial fraction, like xi by u equals to 1 by s minus lambda I. So if we define like this, then you can very easily see that y is nothing but r1 x1 plus dot 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 rn xn plus b. And you are also getting the state dynamics. Xi dot is nothing but lambda I xi plus u. Xi dot is nothing but lambda I xi plus u. What is the benefit of this diagonal form? This is very important to understand. The diagonal form decouples the state dynamics from each other. In the general representation, you saw that x1 dot, any particular x, suppose it is x1 dot is dependent on all the states and the control input. But here we can see that the particular xi dot is dependent on only itself, no other states, and the control input is also coming. So it is very easy to analyze the state dynamics when we represent the system in the diagonal form. And you can see that only one thing that we need to have a knowledge of the eigenvalues or the poles of the transfer function or the roots of the characteristic equation. We need to have that idea. We need to have a knowledge about this. So if we have that knowledge, then our life becomes very simple. We can analyze the system in the diagonal form, and readily we'll be able to calculate the states of the system, the state trajectories. Xt will be able to evaluate from this, y will be able to evaluate from this. So this is very simple, and we can also very easily see that these eigenvalues, these are the eigenvalues, and they are directly impacting the stability of the system. So considering the unforced system, if u is 0 suppose, then lambda I being negative guarantees the stability of this particular state. If it is positive, then this particular state will become unstable. So this is very simple, we all know this. And we also have a control input coming here, through which we can manipulate the evolution of this particular state. There is another way of writing this, where we actually define this a bit differently, and then y becomes a bit different. So this is a ABC representation, and the other representation is where we take the Ri's in the definition of the state dynamics itself, and then y becomes simply the summation of the states. So that's all. So this Ri comes here, which sits with u. So this is another representation. So with all this representation coming from the transfer function, so this is pointing us to one thing, that even though the system may be same, system meaning the transfer function being can be same, but the SPRs, the state space realizations, can be different, and it simply depends on how we define the states, how we choose our states. We have to so the number of states we know, it is n, but how we choose those n states gives us a new form, a new realization. And one realization may be useful in a certain situation to do a certain sort of analysis, and or a certain sort of design, and another form can be useful for some other sort of design. So this is the utility of this is the power that we get when we come to the SPRs, when we come to the state space realization. Now here another question will come to us automatically. So is it possible that we can convert from one state space representation to another? If we are not able to do that, then this power is lost basically, because I am deriving in a certain way by choosing the states in a certain way, and then if I am unable to take it to a representation which suits my analysis and design, then this power of having this another representation is lost to me. So we must have this way of going from one SPR to another SPR. And another question that comes to our mind is that if we have an SPR, then is it possible to go to the transfer function, because transfer function is also sometimes useful for some analysis and design purposes. So let us see the second question first, going from the SPR to the transfer function. And this is very simple. We assume any general, this is a general LTI representation, and from here we simply take the Laplace, we do the Laplace transform here, and by shifting, doing some algebraic manipulation, what we can get XS as SI minus A inverse B US, and YS is CXS plus DUS. So we get ultimately the transfer function as CSI minus A inverse B plus D. So any SPR for a LTI system, if you are given an SPR for a LTI system, that means A, B, C, D are given to you, you can always go to the transfer function by using this formula. And this is for any SPR. This ABCD can be any ABCD. Now the next question we try to answer, which is about the conversion from one SPR to another. So this is very important, and this really gives us the power. So what is the thing here? So let us see. So suppose we have the state space realization in a state space capital X, of which the X is the states, small x are the states here, and we want to take it to another state space capital Z, of which this small z's are the elements. So these small z as well as the small x are the states basically, and they lie on this state spaces capital X and capital Z. So suppose as an example, you have a representation in capital X, you want to go to the diagonal representation which is in capital Z, suppose. So how to go about it? So we have to have actually a relationship like this: x equals to pz, and this p must be invertible or non-singular basically, so that you have this inverse relation also possible. So if you can figure out a p which takes you from x to z, and this p must be non-singular, so you have to figure out a non-singular p which can take you from x to z, then this transformation is possible. Then you can go from the state space x to z and again come back to the state space x when your analysis and design in the z state space is over. So this coming back is also important. So you should be able to come back also, and that has to happen in a one-to-one and invertible manner. And this is only possible when your transformation P, this P, is non-singular. So this is only possible when your transformation P is non-singular. So if you have this non-singular P, then this P is basically called a similarity transformation, because this gives you a similarity between the two state spaces, and you can convert from one state space to another. It is the similarity term. Why this is also called similarity? Because it keeps the transfer function and hence the eigenvalues of the system invariant. So this is an important property of similarity transformations. The conversion between different SPRs should not hamper your transfer function. The basic system must not change. The transfer function and its eigenvalues must remain same. So they remain same if you use a similarity transformation. That means if you have a P which is non-singular and you relate these two states with this P. So if you have this relationship as x equals to pz, then you can derive the SPR in the z state space given the SPR in the x state space. So suppose the SPR in the x state space is this simple ABCD, then z dot will basically be what would be z dot? Z dot is P inverse x dot, and x dot we can write as ax plus bu, so that we have written here, and then we replace x as pz again. So basically your az is P inverse AP and bz is P inverse B. Similarly, when you try to figure out what is the output using the z state, not the x state, then you will see that your C matrix changes to CP, D matrix does not change. So D remains unaffected. The other relationships are given here. We need to be certain. So I have shown you a proof basically that the transfer function remains invariant, and that is all that we need to show, because if the transfer function remains invariant, eigenvalues remain invariant, all the different other properties related to the transfer function all remain invariant because the main transfer function is invariant. So you see here from the x state space we had derived this GS this within the formula if we have ABCD as the matrices. Suppose we want to calculate the transfer function from the z state space. Suppose it is GZS. So we have to use the AZ, BZ, CZ and D matrices here. So using the same formula, CZ SI minus AZ inverse BZ plus D. But your CZ is CP, AZ is P inverse P and BZ is P inverse B. And then you have to do some matrix manipulations like putting this P inverse inside the bracket, and the next step is putting this P inside the bracket. And to do that, you have to know this matrix relationship, that M inverse N inverse is basically N M inverse. So using this relationship, you can do this manipulation and find out that ultimately your GZS is also equals to CSI A minus A inverse B plus D. System properties are still the same. Only what had happened, the way we had defined the states had changed, and that reveals some information, some sort of information in one sphere, some other sort of information in another sphere. And we would like to be in an sphere in which we would in which our analysis and design will become easier for us. How to find out the solution? So here what we do, actually we are doing a solution for the LTI case, x dot equals to AB plus AX plus BU. So we first try to figure out what is the homogeneous, what is the solution of the homogeneous system or the unforced system. So for that, we note that if we have a scalar system, then it basically is e to the power ATX0, which is a summation of polynomials in T. So this is the infinite polynomial in T basically. So we also suppose that this x dot equals to AX, when this is a vector, that will also be a polynomial in T. Why we suppose this? Because this xt, what is xt? This is all x1t, x2t, all these scalars. Okay, so all these scalars are taken together to form the vector. So each scalar will have a solution of itself, and we see that the scalar solution looks like this. So we suppose that each element will also have a form like this, and hence the entire vector will have a form like this, where this a0, ai, etc. are all vectors. T is only the scalar. So if that is the form, then x dot can be easily understood from here. So we simply take a derivative, and since x dot equals to ax, we also figure out what ax will be if x is this, and then we equate both sides. We equate the coefficients in both these equations, and that gives us the relationship between every ai with the initial a0. So only we need to know a0, you see, only we need to know a0. All the other ais will be related to a0. And what is a0? If you put t equals to 0, then a0 is basically the initial states x0. So the initial condition needs to be known. So we suppose that the initial condition is known to us, then we can easily figure out the solution now, because the solution will take this form. So all these a1, a2, etc. are placed here in terms of a0, and a0 is taken out and written as x0, and we see inside the bracket we have this particular polynomial in T, and this polynomial is having coefficient as a. This coefficient as capital A, which is a matrix, and it looks very similar to the exponential solution for the scalar case. So we term this as the matrix exponential, not the scalar exponential, but matrix exponential, and we denote it also as e to the power of capital AT. We call this as the matrix exponential because of the similarity of expression with the scalar exponential. So the solution the solution now basically becomes what? The solution xt is basically e to the power of at x0, and this is having a very analogous relationship with the scalar solution also. So this is very easy to remember for us. We need to have the idea of what is a state transition matrix. So you see the solution is this. what is e to the power of at doing? E to the power of at is basically a matrix. It is a matrix. It is a matrix function and a matrix itself, and it is a time varying matrix. So what it is doing, it is taking the initial states and putting it at some present state. So it is always, as time varies, as t varies, so only your information of the initial state is needed. You don't need to have any other information basically now. So you just need to know the time, and for that particular time you can compute what is xt. You don't need to know any other intermediate values of x. Only you need to know the initial value of x0. So it is simply taking the x0 and transitioning it to the present state xt. So this is called, that is why it is called the state transition matrix. So it is doing a transition of the initial state to the present state. So this is the definition I have tried to write here, and you can read it. So it is simply the operation, the transition of the initial states carried out by the operation of the time dependent matrix function e to the power of at. And in our continuous time LTI case, this becomes the matrix exponential. For other systems, some other function may perform the same operation, that is transitioning the initial state to the present state. It might not be e to the power of at for systems which are not falling under the category of continuous time LTI. For continuous time LTI, the transition matrix is the matrix exponential e to the power of at. For other classes of system, the transition matrix will most possibly not be this. Okay, and you may have already studied for time varying system or discrete system, it is not e to the power of 8, it is something else. But see, we are limiting our scope of discussion for this 1.5 hour duration to LTI, continuous LTI system. We are looking at this particular state transition matrix only. And if my generally it is denoted as phi t, and if my phi t is e to the power of at, then I have several properties coming out for the STM of the continuous time LTI system. What are these properties? So remember that these properties, what I have written down, is only applicable because my phi t is e to the power of at, and you can simply verify this by putting this t equal to 0 in e to the power of at and see that it becomes identity, and you can do the inverse and you see that it is basically phi minus t. And all these properties that I have written down here can be very easily proved from here. Only one thing I will prove with an extra effort, which is this one. So that is important also. So if I move from one system, one state space, A1, B1, C1, etc., to another state space where the matrices are A2, B2, etc. So, and my relationship is like this: A2 equals to P inverse AP. P is the similarity transform, and then the state transition matrices in these two state space relations will also be related to each other in a certain way. What is the relationship? This is the relationship, that P phi, if A2 is P inverse A1P, so you are basically coming to A2 to do some operation. Suppose you find out the solution or you find out the state transition matrix. Then you have to go back to the original representation and see what is the state transition matrix in the original representation. So you have to operate on the state transition matrix of the A2 state space. So that operation is like this. So you can go back to phi A1t from phi A2t by simply doing P phi A2t P inverse. So it is just the opposite. Just the opposite. Now, how you can prove this? This is very simple to prove. So since A2 is P inverse A1P, and your phi A2t is basically this expression, Now you see, note from here, no, note that your PA2 any power k, this k can be any power, P inverse is basically how you can write this. You can include a P inverse P between every successive A2. So there are k number of A2s, right, here. So in between every successive A2, you include a P inverse P. You include a P inverse P. So what happens? You have now k number of PA2 P inverse blocks. K number of PA2 P inverse blocks. And what is PA2 P inverse? It is A1 basically. So you have A1 to the power of k now. Then if you now look at this and you try to do a P phi A2 P inverse, then you are basically what you are doing, you are putting a P in the beginning of each term and a P inverse at the end of each of this term. So let us look at this term. So it is basically 1 by k factorial P A2k P inverse, and that is A1k. So all these basically gets converted to A1 terms, the terms with A1, A1 square, A1k, etc. And that is what? That is nothing but phi A1. So that is the simple proof between the relationship between the STMs of this when we are having two different state spaces related through a similarity transform P. How do we, what is the time now? So let me just see. So, okay. So I have around 20 minutes more, right?
Yes, sir. Yes, sir.
So
Yes, sir. Yes, sir.
I will skip some of the slides and I will point you out to this. So basically coming to the diagonal form is helpful because there the state transition matrix is very easily computed as in this manner. So the diagonal form is basically where the eigenvalues take places in the diagonal, and e to the power of this lambda t, this capital lambda t, is basically or e to the power of small lambda t in the diagonals. So it is very simple to compute in diagonal form. So this I will leave now for the timing, Kelly-Hamilton. But now the solution, the entire solution looks like this. Xt takes the form like this when you have the input also in your input also coming in picture. So previously we are dealing with the unforced system. We figured out that for the unforced system we only have this much as the solution, but if you have the input, then this is the entire solution. And what you need to know here is only this e to the power of 80. The rest is just an integration. So this is the matrix exponential that you need to figure out. So its computation is important. So this is the end of my part 1, and I would like to cover the next part. Let me try to finish it within time. I'm not sure, might spill a bit. So let us quickly go through it. What topic we need to cover? We need to cover controllability, observability, and the controllers, state feedback controllers and observers. So there is the concept of two paired concepts basically of reachability and controllability, where reachability is basically telling us that some state is reachable at some time t1 if we have an input that transfers the state from 0 state to that particular state. So the initial state is 0 and the final state is x1. So we simply need to have some input which would be able to do that. And the system is said to be reachable if this happens no matter what x1 we select. So that means we can reach everywhere in the state space basically. Controllability says that we have to reach to the 0 state from anywhere in the state space. It is simply the opposite concept. So reachability tries to take you from the 0 state to any state, controllability tries to take you from any state to the zero state. So the wordings are placed like that. So it is simply the opposite concept. For continuous LTI systems, reachability and controllability mean the same thing, but it is not so for in general for other systems. And if the system is reachable, it is always controllable. That is also true, but it is not it doesn't hold the other way around. So what we are interested in the controllability property actually, because we want to come to a specific state. Here in the definition it is called zero, but it is basically without loss of generality we are calling it zero, because you are fixing a particular state. If you fix a particular state, you can always subtract it from your entire reference frame and come to zero. So zero is without loss of generality. So our aim is basically to reach a particular state starting from any initial condition. So we are basically interested with the controllability problem. However, to establish the property of control, to check whether a system is controllable or not, we would be using the reachability condition. For LTI systems, both are same, so it does not matter. How we are using the reachability condition? So as per the concept of reachability, we have to reach any state xt1, and we simply what we do, we start from zero. That is also another thing, and we expand this. When we expand this in terms of your what we have done, we have expanded this e to the power of a t1 minus tau, and it forms some infinite series. Now we to prove this, we actually use some concept about basis of state spaces. I will not dig deep into that, but whatever actually the condition comes out is basically this, that this particular matrix will need to be full rank, and I have proved this also here, so later on you can go through this. It's not a very difficult proof if you understand what about dimensions and basis, etc. So it is not a very difficult proof. However, the final thing that comes to us is that we need to form this matrix and check the rank of that matrix. That should be equal to n, which is the order of the system. So if it is so, then I can say that the system is basically we have tested reachability, but since we are dealing with LTI system, we can also say the system is controllable. And observability is simply a dual property actually, and it has a parallel concept called reconstructibility, and this is like this. The definition goes like this: the system is completely observable if for all t1 there exists t0, such that by observing the output at t1, the initial state can be uniquely determined. So here in observability, we are trying to determine the initial state by observing the present state. And this t1 actually can be anything greater than t0. So at any instant other than t0, so in the future of t0, we observe y and we are able to determine what is the initial state. What is reconstructibility? Here we observe the initial output and observe the future state. So it is simply the opposite thing. What we are interested with? We are interested with reconstructibility, because we are not having the presence. Sometimes what happens, we want to figure out the state. We want to estimate the state of the system. So all the states are not available for measurement always, and sometimes we define the states also in a certain way that they are not possible to measure. So we have to estimate the states. But estimating the state means at this particular time I want to know what the state of my system is. What information would I have with me? I would have information of the past outputs only, right? So with the help of these past outputs, I should be able to construct the state at this present instant. So we are actually concerned or about this reconstructibility property. We are interested in the reconstructibility property. However, when we are trying to figure out what is the condition for reconstructibility, we would actually figure out the condition for observability and conclude with it that my states are also reconstructible. And to do that, we use the definition of observability, and going through some proof, we would see that this is the condition which is required, that we form a matrix like this: C, CA, dot 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 CA n minus 1 transpose, and this matrix is called the observability matrix. That should be full rank. That means its rank should be equal to n, which is the order of the system. There is a relationship of the similarity transformation from C and O. What is the relationship? So let us suppose that there are now two representations, two SPRs who are which are having A, B, C, D, and A bar, B bar, C bar, D. So, and in one SPR, the controllability matrix is C or observability matrix is O. In the other one, the controllability matrix would be C bar, observability matrix would be O bar. So with that assumption, so I have these relationships like this: A bar is P inverse AP, B bar is P inverse B. Then it is very easy to show that C bar, which is basically B bar, A bar, B bar, etc., etc. So we simply write B bar as P inverse B and A bar as P inverse AP, and then we see that this P inverse from inside will get cancelled out, and I can take this P inverse outside. So only this P inverse will stay there, and you can take this outside. And this is basically what? This is basically the controllability matrix in the ABC state space. So this is the relationship that we get is like this. Or from here, since we similarity transformation by default means that P is invertible, so we can evaluate this P as C bar inverse. Similarly, if we have the observability matrices, we can say that the P is basically O bar O inverse. This is also something that we can prove actually. So if we know the controllability matrix of the SPR where we are presently belonging, if we know the controllability matrix of the SPR where we want to go, then we can compute the similarity transformation which will take us there. Same thing for the observability matrices. These two are dual systems. The controllability in system S1. So if we have two dual systems is basically the dual of ABC is A transpose C transpose B transpose. So that is the dual of the system ABC. So in these two systems, the controllability matrix of this system is basically same as the observability matrix of this system. The observability matrix of this system is same as the controllability matrix of this system. This is also an important property between dual systems. So that is proved in this table. You can easily see that. I will not spend much time here. Next thing that I want to focus is this particular thing. I will skip some slides. Basically, I think I can go straight now to state feedback controller. So the design aspect, actually, I can go straight into it. So the design aspect means I want to design a particular controller for my system. So what is my intention? My intention is normally to make my system stable, or if it is a regulation problem, I want to make the error system stable. So whatever, if it is the state space, or if it is the error space, whatever, we can always represent it in this manner. And we are now focusing only on the state space. So here what we need to, what our intention is, our intention is to design a controller U so that this dynamics x dot equals to ax plus bu becomes a stable dynamics. So the first proposition is we choose a linear state feedback controller. Linear state feedback controller means the controller is dependent on the states linearly. So we choose u equals to minus kx. So when we choose u equals to minus kx, then x dot becomes a minus bkx, and xt can be easily evaluated like this. So this we already have seen. So this is simply like a closed loop A, right? And it becomes a homogeneous system or like an unforced system, and we know the solution of the homogeneous system. So it is e to the power of a minus bk. A t is missing here, sorry, a t should be here, time t, so into x0. What we need to do only, we need to fix the eigenvalues of this closed loop matrix A minus bk in the left half of the S plane, because this is a very well known property of stability of homogeneous systems, that the A matrix, this matrix, if x dot equals to ax, the A matrix eigenvalues must be in the left half plane. So here the matrix is A minus bk, so the eigenvalues of the closed loop state matrix A minus bk must be in the left half S plane. So are we able to do that? Can we do that? So that is the question. So what we have with us is this matrix, is this gain k. A and B are given from the system, so we cannot do anything to it. We are from the outside, from externally, we are supplying the controller, and this gain k comes into picture, which we can actually provide the system in order that we can make it stable. So is there any restrictions that we will be able to, that we have to meet so that we can make it stable? So let us investigate that. So the condition is basically this, that A-B pair must be completely state controllable. That means the controllability matrix found by this A-B pair must have full rank. How to prove this? We are simply going ahead with the design, and that will also give the proof. So let us suppose we are able to take the system to this particular form. Any system, we are having any system in a state space X, but we are coming to this particular form, which is called the controller canonical form, which has this particular form of A and B. So the form of A and B in the controller canonical form is known to us, and there we assume that we are able to take the state from our given state space to the controller canonical state space. So the state transition matrix is P. So the relationship is like this, P inverse AP, etc., etc. We also suppose that the gain that we would design in this case, in this controller canonical form, Kc is equals to Kp, where K is the gain that we should have designed in the original state space. We check out that AC minus BC Kc. So this is the closed loop state matrix in the controller canonical form, because Kc is the gain that we are supplying in the controller canonical form. So AC minus BC Kc basically is P inverse AP minus P inverse BKP. So it is basically P inverse A minus BKP, like that. And the characteristic polynomial for this is Si minus Si minus A inverse, Si minus A, determinant of Si minus A. What is A? A is entire this thing. And here this I we can write as P inverse P, and hence we can combine this entire thing like this, and we basically get the determinant of Si minus A minus Bk. That means the characteristic polynomial, what does it give? It gives the eigenvalues of this particular matrix. So the eigenvalues of this matrix, which is a closed loop state matrix in the original state space is same as the eigenvalues of the matrix this, which is the in the controller canonical state space. So choosing this Kc as Kp enabled us to come to this conclusion. Please note that choosing this Kc as Kp enabled us to come to this conclusion. So now we can choose this Kc, we can design this Kc, and the design of Kc is easy in the controller canonical form. That's why we have come to the controller canonical form. So if we make AC minus BC Kc, simply we see that this last row, these A terms are getting modified by these K entries, and nothing else happens. Nothing happens in any other part of the state matrix. So the form of the state matrix remains same. The entire form of the state matrix remains same. It does not change. And we can simply see that the characteristic polynomial will simply be putting these coefficients with the S, and we are getting the characteristic polynomial. And if we have the desired locations, pole locations as lambda, so we can get the desired characteristic polynomial. We can evaluate, and we will see that the coefficients of all these S terms, it will come out, and suppose it is C1. So C1 is known to us from our desired location of the eigenvalues. A's are known to us from the system. K are what we want to provide in order that we have the closed loop characteristic polynomial same as the desired characteristic polynomial. So here you can see easily by comparing coefficients, we have this relationship that Ki would be Ci minus Ai. And hence I am able to get the Kc matrix, and then I will be able to get the K matrix. So obtaining the K matrix, my P must be invertible, and P being invertible basically would mean that the controllability matrix in the original SPR must be invertible, because the controllability matrix of the controller canonical form is always of full rank. So P being full rank, CC being full rank, C must also be full rank in order that we are able to do this operation. So that is the condition that my original system, original SPR must be controllable in order that I can form a state feedback controller and place eigenvalues at any desired location. There are other methods of finding out this K, so I am not discussing that. So this is another important thing, another design from the design aspect, the full state observer. So the idea of the observer is this, that the states, I have already told this, the states are not always measurable, because they even if they are some physical variables of the system, they may not be always measurable. And sometimes we define the states as some variables which are not having any physical direct physical interpretation or direct physical observance in the system. So there may be some virtual variables also. So we are not able to measure them as such. So what we can do best, we can estimate them. So there is this idea of estimation which we utilize. So how we do it? We do it through an observer. So observer is basically the observer is basically a dynamical system which observes the states of the original system or estimates the states of the original system. So the linear observer is designed by simply copying the original dynamical system, the state equation only, and introducing a correction term. So you see, of course the state is not x, because x is unknown, it is x hat, and this sits in a computer basically, and we can initiate it from any x hat 0. So this system becomes completely known to us, and we only supply a correction term like this. So for the linear observer, the correction term is L y minus C x hat, and this makes it like this. So now we construct the error of the state. So error between the actual state in the system and the observed state from the observer. And the error dynamics, you can very easily find the error dynamics by E dot equals to X dot minus X hat dot. By using these two equations, you will be able to find that the error dynamics is A minus LCE. So this is now the problem. Now our intention is to make this error converge to 0. Then only I will have X equals to X hat. That is what I need, that my observed state will be equals to the actual state. So we need E equals to 0. So we get this particular dynamics of E, and what we need, we want to place the poles of the characteristic polynomial of this particular matrix. That means we need to place the eigenvalues of this particular matrix in the left half S plane, of course. Are we able to do that? And what is the condition when we are able to do that? So for that, we look at the dual system. So the dual system is AT, CT, BT. And in the dual system, if I choose a state feedback gain as LT, then I can design AT minus CT LT only when this AT CT pair is controllable. That we have already proved in the state feedback controller. So if we have if we have A minus BK, then we are able to design K if AB is controllable. So in this case, if we want to design LT so that we can place the eigenvalues, then AT CT must be controllable. So now you see that this is one observation, that AT minus CT LT transpose is basically A minus LC. That means wherever you place the eigenvalues of this particular matrix, the eigenvalues of this particular matrix will also be placed in the same place, because eigenvalues of the transpose matrix is also the same as the initial matrix. So the necessary and sufficient condition, what is it? It is simply AT CT being controllable. That means what? That means AC is observable. So that is the dual property. So AC being observable is our condition in order to form the full state observer. This is the last slide I have. It is simply a verification that introducing the observer in the loop does not affect the dynamics of the entire system, and it does not affect the design of the controller. So how we can prove it? Now you see, we are now designing the controller not using the actual state X, but the observed state X hat, because this is what we have with us. This is given by the observer. So now we place this X hat in the original system. So the original state system dynamics looks like this. But X hat, what is X hat? X hat is basically X hat is X minus E. So we put that here and we get this particular equation. So now your X dot is related to X as well as the error E. And the error dynamics, we know it is like this. So now we augment the state dynamics with the error dynamics and form a total dynamics of the actual state as well as the error. And this is the system that we get. This system, you see, it is beautifully partitioned, and the characteristic polynomial of this characteristic equation of this dynamics is basically determinant of Si minus Si minus A minus Bk and Si minus A minus Lc. And you see that the eigenvalues of this matrix and this matrix does not interfere with each other. So we can design this separately, and still the eigenvalues of the complete dynamics will be the eigenvalues of this observer and the controller that we had designed. So they will remain separate and they will contribute to the complete dynamics. So with that, I end the lecture, and thanks for your attention. So if you have any questions, you can come out with them, and let me try to see. I have successfully completed in time, though I had to skip some of the slides. I'll try to answer the queries, whatever I'm receiving.
Yeah. Yeah. Thank you, sir. So participants, have you any queries?
I hope you can see me now. You are listening to a blank voice probably all this time.
Yeah, from the participants. Yeah, if you have any queries, sir has started from very basic, from the concept from the state space, and he has elaborated the difference, that is observability, reachability, controllability, constructability. So these are the some the properties that can be used in our advanced control system, also in different research also. So if you have any query regarding your any point of view, then you can ask. Yeah, from the designing of controller or observer. So I think participants have not any queries. So sir, you have just I have one query. When you have say that reachability and constructability. So, sir, can these property when system is not controllable? So, in some research papers, we have seen that they have just assumed that system is reachable. So, according to that, that means in that system, whether although it is not observable, but and not controllable, but they will assume the property of reachability and constructability in that sense. So, is that in
Because
some yeah.
Sometimes what happens that as I told you, for only for continuous LTI system they mean each other.
Okay.
For other systems they might not mean each other, and we have to really see what our intention is. If our intention is to have controllability, then controllability needs to be satisfied. If our intention is something else, then we have to see if that particular condition is satisfied or not. So sometimes what we see that even if the system is not controllable, it can be there are two other terms which I have not mentioned in this lecture. One is stabilizable, and so if the system is not controllable, even then it might be stabilizable. So I am interested basically in stabilizing the system. So if my system is stabilizable, I don't need to go to controllable. Controllable will all mean stabilizable. If the system is controllable, I will be able to stabilize it. However, even if my system is not controllable all the time, for all the eigenvalues, for all the modes, basically we call them modes, for all the modes, if the uncontrollable modes are already stable, if the uncontrollable modes are stable by themselves, then the system is stabilizable. We can actually partition between controllable and uncontrollable modes. Those things I have not covered in this lecture. And similarly, for observability, the condition is detectability. So if we have detectability, then even though the system may not be observable, we can still construct an observer to estimate the states.
Okay, thank you, sir. Sir, we have one query you can see in chat box from Shubhajit Bhattacharya. How controllability is measured for time varying system?
Okay, the definition remains same. So that is the power of definition. As Shyam sir also have told you, the definition will remain same. You have to now figure out that what is the condition for the particular system, so that I can have the definition coming through. Okay. So here in the slides I had mentioned, but I had not time to go into that. You will have the slides and you can look into that. We had proved that this is the particular condition so that my system will be controllable. So I have the idea of what I mean by controllable, what I mean by my system being controllable. Actually, we have used the reachability property. So we know, we have the idea of what we mean by reachability, and we use that idea to figure out a condition which comes from the structure of the system. Similarly, you will be able to figure out a condition which comes from the structure of the time varying systems, which will give you the condition of the system being controllable or reachable, or whatever you want, whatever condition you want to figure out from that system. So it will depend on that particular system that you are talking about. So normally time varying, we have to look into that system and figure out what would be the condition. So the condition for controllability, observability, very well defined for linear time invariant systems. For other systems, it might be case to case basis, it might be system to system basis. We have to work and figure out how we can deal with the system.
Okay, thank you, sir. So if you have any other queries from the participant side, so I think no other queries. So with this, just I wind up this session. Thank you so much, sir, for sharing your valuable time with us, and also for sharing your great knowledge with us. Thanks a lot, sir. Thank you very much, sir.
Thank you. Thank you, NIT Silchar, also for inviting me. And it was very nice to present in front of all you.
Thank you, sir. We are very grateful to you. Thanks a lot, sir.
Thank you. So I can leave the call now?
Yes, sir. Yes, sir. You can leave, sir. Thank you, sir.
Okay. Okay.
Yeah, participants. Yeah, we have next session from 2:30 to 4. In that session, we will discuss about the recent trends in nonlinear dynamics, chaos, and engineering application. So we will meet on 2:30 sharply. So be online with 5 minutes prior to that. That means we will expect that all of you will join 2:25. Okay. Thank you. And thank you so much. Yes, link will be the same for all day. Okay. Already we have mailed you all the schedule, program schedule. So today evening, again, we will send the program schedule to all of you for the whole days. Okay. Thanks a lot.
Feedback link, please. Feedback link, please.
So, dear Shah Rashil, you have just joined. Actually, our session 5 has been completed, and I think a feedback link has been closed for session 4. So, I think you have attended this session on YouTube.
Yes, sir.
Okay. We will provide the links for the feedback at the last of next session. Okay. So don't
Sir,
be
for
worried.
fifth session.
Yeah.
For fifth session.
Yeah. Yes, we will provide. Okay. No issue. So don't worry about that. We will provide the links. Those who have not filled for any issue. So we will provide those students or those participants to link after the completion of the session 6 feedback. Okay.
Okay, sir.
Yeah. Okay, Sharasim. So you are attending our YouTube channel. Okay.
Yes, sir. Sir,
Okay.
many of the participants are asking for in the YouTube chat box.
Okay. Actually, yesterday I think you have got the mail for Google Meet link,
Yes,
isn't?
sir.
So,
Yes, sir.
so you must all have to join here. Okay, no issue.
Oh,
We will provide the feedback at there also. Okay, no issue.
okay.
One of the participants have told me that some are watching there, so I will also provide there. Okay, no issue. Thank you,
Okay,
Rasil.
sir.
We will meet at 2:30. Okay, sharply. So you will.
Yes.
We are expecting that you will join 2:25.
Yes, sir.
Okay, thank you.
Yes, sir.